The deep dive is back, and today we are wading into, well, a pretty deep theoretical conflict. It's something that's really bothered physicists for almost 50 years now.
Yeah, it's this fundamental clash, isn't it? The ultimate grudge match, as you put it. It pits the rules of the quantum world, against the rules of the cosmos, general relativity.
Exactly, and we're going to be investigating a really radical proposed solution to what's known as the black hole information paradox. It's a complex idea called the quantum memory matrix, or QM for short.
And this deep dive, I think it's crucial because this paradox, it's not just some small technical issue. It's a sign of a fundamental breakdown, right? Where our two best theories of reality, quantum mechanics and general relativity, have to somehow meet.
And this QMM idea, if it holds water.
Well, if it's correct, it wouldn't just solve the paradox, it would fundamentally change our understanding of what space-time is.
Okay, so let's set the stage. Lay out the battlefield, maybe. First corner, we've got quantum mechanics, QM.
The playbook for the very small.
Right. Particles, probabilities, things being in multiple starts at once,
Yeah.
superposition. And the absolute bedrock principle of QM, the most sacred rule, is unitarity.
Unitarity, information conservation, essentially.
Yeah, it basically guarantees that information, the quantum details of a system, is never truly lost. You know, you could take a whole library, shred the books, burn them, scatter the ashes.
Yeah.
But in principle, the complete information about the original quantum state of those books must still exist somewhere in the smoke, the ash, the heat, the whole resulting system. It can't just vanish.
It can transform, it can get scrambled, but it can't be deleted from the universe's ledger.
Precisely. Okay, other corner, general relativity, GR.
Einstein's masterpiece. Gravity isn't a force in the usual sense, it's the curvature of space-time itself, caused by mass and energy. And GR describes black holes incredibly well, classically speaking.
And classically, black holes are almost absurdly simple, right? The no-hair theorem.
Famously simple. Defined only by three things you can measure from the outside: their total mass, their electric charge, and how fast they're spinning their angular momentum. That's it.
No matter what falls in a star, an encyclopedia, a guinea pig, its complex information, according to GR, just gets wiped clean, leaving only those three numbers.
And that's where the conflict starts to brew. You throw complex quantum information into the black hole.
And the no-hair theorem seems to say, poof, that information is gone, erased from the external view.
That's really only the first shoe to drop. The second, and maybe even more problematic one, is Hawking radiation.
Ah, yes, Stephen Hawking's discovery. Black holes aren't perfectly black.
Not quite. Due to quantum effects right near the edge, the event horizon, they have to emit radiation, and that this radiation causes them to lose mass, to slowly, well, evaporate over immense timescales.
And crucially, this Hawking radiation is described as thermal. What does that mean in this context? Like generic heat, random noise.
Exactly like random noise. Think of black-body radiation, like the glow from a hot piece of metal. It has a temperature, but the individual photons coming off don't carry any specific information about what made the metal hot.
It's just statistical.
Purely statistical. It's characterized by a temperature, the Hawking temperature, T sub H. We don't need to go through the whole hapula now, but the key part, as you hinted, is that it depends only on the black hole's mass, charge, and spin, those no-hair properties.
So wait, let's unpack that formula maybe just a bit. The Hawking temperature, TH$.
Okay, so THLE equals, let's see, Planck's constant times the speed of light cubed, that's d power c3 we are, all divided by 8 pi, times the gravitational constant g, times the black hole mass m, times Boltzmann's constant KLR.
Right, so TH, 5RT, HEM key would be the important thing isn't memorizing that, but
But noticing the m, the mass, is in the denominator.
inverse relationship.
Exactly. THLR is inversely proportional to mass. So smaller black holes are actually hotter. They radiate more intensely and evaporate faster.
Okay, so here's the full paradox then. A black hole forms, swallowing loads of quantum information. It then slowly evaporates by emitting purely thermal, information-free Hawking radiation. Eventually, maybe after trillions upon trillions of years, the black hole evaporates completely. Nothing is left.
According to the standard picture, yes.
So where did the original quantum information go? The thermal radiation didn't carry it out. The black hole itself is gone. It seems like the information has been permanently destroyed.
And that is a catastrophic violation of unitarity, the core principle of quantum mechanics. If information can be destroyed in black holes, quantum mechanics itself is fundamentally flawed.
The stakes couldn't be higher, really. It's about the internal consistency of physics itself.
Which brings us finally to the quantum memory matrix. the QMM hypothesis.
Instead of trying to find the information hidden in subtle correlations in the Hawking radiation, or maybe escaping through wormholes or stored on some distant boundary, QMM takes a really different approach.
It proposes something radical. Spacetime isn't just the stage where physics happens. It's an active participant. It's a dynamic quantum information reservoir.
Spacetime itself remembers.
In quantum sense, yes. Our mission today is to really unpack this QMM framework. We want to get into the details. How does it propose quantizing spacetime? What exactly is a quantum imprint?
And crucially, how does it offer a concrete, step-by-step, unitary mechanism, meaning information preserving, for getting that information back out? How does it resolve the paradox while trying to respect both QM and GR?
That's the goal. Let's dive in.
Okay, section 1 in the sources, the foundation of the QMM hypothesis. It starts, as it must, with quantizing spacetime itself. You can't just bolt quantum effects onto a classical background here.
No, you have to go deeper. General relativity treats spacetime as this smooth, continuous fabric. But QMM, like some other quantum gravity approaches, starts by saying, no, at the very smallest scale imaginable, the Planck scale.
Which is tiny, right? Like 1035 meters,
Right.
incredibly small.
Absurdly small, the Planck length, Eleanors. At that scale, QMM posits that spacetime is discrete. It's granular. It's broken up into fundamental indivisible units. The sources call them spacetime quanta or quantum cells.
So forget the smooth rubber sheet analogy. Think more like a digital screen made of fundamental pixels, but for reality itself.
That's a great way to picture it. A cosmic tapestry woven from individual threads at the Planck scale.
Okay, if spacetime is made of these quantum cells, then each cell, each pixel, $6, must have quantum properties.
Exactly. Each cell, $6, isn't just a location. It's associated with its own mathematical space of possible quantum states. This is called a Hilbert space, denoted sic up to leisure. And crucially for QMM, this Hilbert space is finite dimensional.
Finite dimensional means it can only hold a limited amount of information, unlike a continuous variable.
Precisely. Each cell has a finite capacity to store quantum information. And the state of the entire spacetime fabric, the QMM, is then described by the combined quantum state of all these individual cells.
Mathematically, how do you combine them?
You use what's called a tensor product. The total Hilbert space for the QMM, let's call it HQML, is the tensor product of all the individual cell Hilbert spaces, HQMM beta times HXC. It represents the vast state space encompassing all possible configurations of the granular spacetime.
This sounds, as you mentioned, like it shares DNA with theories like loop quantum gravity or causal set theory. They also start with a discrete structure.
It absolutely shares that foundational idea. And this is a major strength, because building spacetime from discrete units immediately solves a huge problem that plagues standard quantum field theory, or QFT.
We're talking about infinities, divergences.
Exactly. In standard QFT, you assume space is continuous. When you try to calculate interactions happening at very small distances or very high energies, the math often breaks down and gives you infinite answers.
Because you can zoom in indefinitely, cramming infinite energy into a point.
Sort of, yes. You integrate over arbitrarily small scales. But if spacetime itself has a smallest possible unit, the Planck sellers, then there's a built-in cutoff. You simply cannot have distances smaller than L upon.
It acts like a natural regulator.
Precisely. It provides an intrinsic ultraviolet or UV regularization. Those calculations that used to diverge things like vacuum energy or self-interactions of particles now yield finite, physically sensible results because the discreteness prevents the infinities. This is a massive advantage for QMM.
So the very structure needed to store information also helps fix fundamental mathematical problems in QFT. That's elegant.
It is. And this granularity isn't just abstract math. It has physical consequences for geometry itself. Things we usually think of as continuous, like length or area or volume, become quantized.
Meaning they can only take on discrete values, like energy levels in an atom.
Exactly like that. Geometric operators, say for length area had or volume had eBay, now have discrete spectra. Their possible values are determined by quantum numbers, integers basically, and scaled by the Planck length, and this other factor, the Barbero-Emirzi parameter, gamma.
Okay, wait. The Barbero-Emirzi parameter. Let's quickly unpack that. What is it and why does it pop up here?
Right, so gamma dou is a dimensionless constant that appears naturally in theories like loop quantum gravity, which QMM borrows from conceptually. It essentially relates the quantum states of the geometry to the size of the fundamental quanta of area or volume.
So it affects how big the pixels of space-time are, in a quantum sense.
In a sense, yes. It's a free parameter in the theory itself, meaning it's not predicted from first principles. Its value has to be fixed by matching the theory to known physics.
Known physics like
Black hole entropy, specifically the Beakenstein-Hawking entropy. You choose the value of gamma, which turns out to be a specific number, around 0.2 something, to make sure that the calculation of entropy based on counting these discrete geometric states matches the famous result that entropy is proportional to the black hole's area.
Ah, okay. So it's a crucial tuning knob to connect this microscopic geometric picture back to the macroscopic thermodynamic properties of black holes we already sort of understand.
Exactly. It ensures consistency. So that's the stage. A discrete, granular spacetime where geometry itself is quantized.
Now, the crucial mechanism, the quantum imprint. This is where space-time stops being passive.
This is the core idea. A quantum imprint, let's denote it by the operator head S, is the physical record, the memory, of a quantum event that happens at or interacts with the space-time quantum cell, the cellar.
So space-time isn't just the container, it's the recording medium. How does the recording actually happen? What triggers an imprint?
When any quantum field, think electrons, photons, whatever, represented generally by half E, interacts at a location 6Ds, the interaction isn't just happening on the space-time stage. It's a transaction with the stage itself.
Okay.
The interaction causes a change, a transition, in the quantum state of the local space-time cell, half X. The imprint operator is basically the mathematical object that describes how that state changes, and it depends on the details of the interacting field.
What kind of details? What information gets stored?
It depends on the specific model, but the sources give examples. The imprint operator half-sac could be a function, let's say $5. It depends on the field value. At that point, maybe it's derivatives, partial mood hacks, which relate to its momentum or energy flow. Perhaps it's conjugate momentum, even powers like half-2, representing energy density.
So things like the field strength, its energy, how it's changing.
Exactly. The idea is that the imprint operator, partial mu-Hanfi, takes these local properties of the field and encodes them into the state transition of the space-time cell, sexton of S. Think of it like writing metadata, the field's properties, onto that specific pixel of space-time whenever an interaction occurs there. The Doppelzahler G1, G2D2 terms in the example form are coupling constants that determine how strongly each property gets imprinted.
So every interaction everywhere leaves a little quantum smudge on the fabric of reality.
A quantum imprint, yes. A permanent record stored locally in the space-time structure.
Okay, this is a profound shift. But now, how do we ensure this whole combined system fields plus the memory matrix still obeys quantum mechanics' most basic rule? Unitarity, information conservation.
That's the absolute linchpin. If this interaction between fields and space-time itself could lead to information loss, we'd be back at square one. The solution lies in the total Hamiltonian of the system.
The Hamiltonian being the operator that dictates how the system evolves in time. For unitary evolution, the Hamiltonian must be Hermitian.
Correct. So the total system isn't just the fields anymore. It's the fields and the QMM. The total Hilbert space is the tensor product, O times HQM.
Combining the state spaces of both parts.
Yes, and the total Hamiltonian Hake-Reichen governing this combined system must have three parts. First, Hake fields, which is just the standard Hamiltonian describing the dynamics of the quantum fields themselves, their kinetic and potential energies, etc.
Standard QFT stuff.
Right. Second, HQMM, which describes the internal dynamics of the space-time quanta themselves. How a cell might evolve on its own or interact with its neighboring cells. This could involve terms like summix for individual cell dynamics and sumlatenable axis wrangles for interactions between adjacent cells 6-6.
So spacetime itself has its own internal evolution.
Plausibly, yes, though the details might be complex. But the third term is the absolutely crucial one, the interaction Hamiltonian. This is the bridge between the fields and the spacetime memory.
This is where the imprinting happens.
This is the imprinting. The sources give its form, like equation 8, acted at a 0.6 dagger looks something like has dagger plus has dagger. Let's break that down.
Okay, Astigas is the field operator.
It annihilates a field quantum at 6 dagger, creates one. Hess-daggers is the imprint operator we discussed. It acts on the QMM state in cell. 6 dagger, X dagger, X dagger is its Hermitian conjugate, its reverse operation. The tensor symbol means these operators act on different parts of the combined Hilbert space Hatz-Dagger on the QMM part.
So the first term, Hatz-Dagger, sort of says, if you destroy a field particle at X, you apply the reverse imprint operation to the spacetime cell there.
And the second term, Hatz-Dagger, says, if you create a field particle at X, you apply the imprint operation to the spacetime cell.
It directly links field creation annihilation with state changes in the QMM.
Exactly. And the crucial thing about this structure, having both the term and its Hermitian conjugate added together, is that it guarantees the interaction Hamiltonian Hatter is itself Hermitian.
Ah, and since Hadage shields and HQMM are also Hamiltonians and thus Hermitian.
The total Hamiltonian Hadfields plus HadQMM plus Hadagit is guaranteed to be Hermitian.
And a Hermitian Hamiltonian means?
Unitary evolution. The time evolution operator generated by Hadagit will be unitary. Information is conserved for the total system. It might move from the fields into the QMM states or back again, but the total amount of information remains constant. It's never destroyed.
Okay, so section 1 lays out the architecture. A discrete space-time built from quantum cells, each cell acting as a memory location via quantum imprints, and a combined evolution rule that rigorously guarantees information is never lost, just potentially transferred into the space-time fabric itself.
That's the foundation. Now we apply this machinery to the ultimate stress test, black holes. Section 2, black hole dynamics encoding and retrieval.
Right. Let's start with the encoding phase. Matter collapsing to form the black hole.
Picture a massive star collapsing under its own gravity. As it implodes, the conditions near where the event horizon will form become extreme. Immense gravitational forces, incredible energy densities.
The curvature of space-time becomes intense.
Extremely intense. And according to QMM, this intense local curvature and energy drives a very powerful interaction between the collapsing matter field and the local space-time quanta, the QMM cells right there. This is the moment of maximum imprinting.
The information about the collapsing star gets stamped onto the space-time fabric as it forms the singularity and horizon.
Using the interaction Hamiltonian we just discussed, the sources even consider a simplified case, say where the imprint is just proportional to the field itself, opportunities being a coupling constant.
What does the interaction look like then?
Plugging that into the general form half-thix half-these O times half-each, and assuming half-ease is Hermitian for simplicity, like a real scalar field, you get something like half-ease OG sum half-ease Eike, summing over the relevant cell's sex efforts. It represents a strong localized coupling.
Okay, and what's the physical consequence of this strong interaction during collapse?
The key concept here is entanglement.
Ah, quantum entanglement. Spooky action. Well, not at a distance here, but spooky correlation.
Exactly. Imagine the initial state of the collapsing matter. It's described by some quantum state, maybe a superposition of different let's call it PA fields, Sarah's wrangle, and the space-time, before the collapse really gets going, is maybe in some simple ground state. Their orangle QMMM, they start separate.
Uncorrelated.
Right. But as the collapse proceeds, the interaction term Henschik kicks in strongly. It couples the field degrees of freedom and the QMM degrees of freedom. The result is that the final state, after the black hole forms, is no longer separable. It's an entangled state of the form KEX-DUMM state ring.
So the information that was originally just in the field coefficients, the Teich's rounds, is now shared. It's encoded in the correlation between the matter state, which is now inside the horizon, and the state of the space-time quanta near the horizon.
Precisely. The information hasn't vanished. It has been transferred via entanglement into the combined state of the system, with a significant part now residing in the configuration of the QMM cells near the horizon. The information is stored inside the combined system.
So the black hole can still appear hairless from the outside in the classical sense, mass, charge, spin, but microscopically, the space-time geometry near the horizon is now incredibly complex and information-rich due to these stored imprints.
That's the QMM picture of encoding. The information is safe, just hidden within the quantum structure of space-time itself.
Okay, encoding complete. Now the really hard part, retrieval. The black hole evaporates via Hawking radiation. How does QMM get the information back out? This is where standard physics breaks down.
This is the crucial step where QMM has to differ from the standard picture. In the standard view, Hawking radiation arises from quantum fluctuations near the horizon. Virtual particle-antiparticle pairs forming, one falling in, the other escaping.
And the escaping one is just random thermal noise.
QMM says, not quite. Yes, particle creation happens near the horizon. But the escaping particle, before it gets away completely, must interact with the information stored in the QMM cells right there at the horizon.
It has to read the memory before leaving.
Essentially, yes. This interaction is mediated by what the sources call the cumulative imprint operator, denoted HADI-HR.
HR for Hawking radiation, presumably.
Presumably. And HADI-H is conceptually just the sum, or perhaps a more complex combination, Of all the individual quantum imprints that were stored in the QMM cell's $6 located at or very near the event horizon dollars. So the HHG looks rexes at the horizon. It represents the total stored information accessible at the horizon.
Okay, so this HHR holds the memory. How does the escaping particle interact with it?
Through another interaction Hamiltonian, specifically for the retrieval process. Let's call the creation and annihilation operators for the outgoing Hawking radiation modes antag and hettai, where time labels the mode, like its energy and momentum. The retrieval Hamiltonian, equation 9 in the sources, looks like het K doing it. This looks structurally similar to the encoding interaction. Let's parse it. Gamma di is some coupling strength for mode Geller. Right. The first term, gamma capture, suggests that creating an outgoing particle, action of stagger, is coupled to applying the imprint operator, reading the memory.
And the second term, gamma catch dagger, couples destroying an outgoing particle, action of Hashin of hatch jagger, maybe writing back or erasing. The key is the coupling between the radiation field and the stored memory.
Exactly. This interaction term ensures that the state of the outgoing radiation is not independent of the stored information. As the particle is emitted, its state gets modified, gets modulated by the information encoded in HHG. The information is transferred from the QMM back to the escaping quantum field.
So the Hawking radiation isn't purely thermal noise anymore. It's thermal noise plus the retrieved information superimposed onto it.
That's the claim. And the sources provide a really nice, simple model to illustrate how this transfer can be perfectly unitary, fully reversible. It involves just a two-state QMM system.
Okay, yeah, let's walk through that example. Equations 3637, figure 6. This feels like the core aha moment for how retrieval works without losing information.
Imagine the relevant QMM memory near the horizon is simplified down to a single quantum bit, a qubit. It can be in-state zero-angle QMM, representing the ground state, no information stored, or state $1 angle QMM, an excited state holding one bit of information that was previously imprinted.
Okay, one memory cell, two states, and we're looking at one specific mode of Hawking radiation trying to escape.
Let's say the radiation field for this mode starts empty in its vacuum state, which we denote zero angle HRM. So initially, let's assume the memory cell does hold information. The combined state of the system is radiation vacuum, memory excited. Right. In a $0 angle QMM, one angle QMM.
Got it. No particle yet, but the memory is on.
Now, the retrieval Hamiltonian heat retrieval we just discussed starts acting on this state. What does it do? It couples this state to the other possible state, radiation excited, memory ground state. That's $1 angle QMMM.
Where the memory is now off, but a particle has been created.
Exactly. The Hamiltonian causes the system to oscillate between these two states. Lugger and go, one angle QMM and $1 angle QMN. It's like a quantum seesaw.
So the probability of finding the system in the initial state starts to decrease.
While the probability of finding it in the final state, particle out, memory erased, starts to increase. We're literally watching the information, the one state, being transferred from the QMM cell to the Hawking radiation particle.
Is the transfer complete? Is it perfect?
In this simplified model, yes. The mathematics shows that the system evolves unitarily. At a specific time, $2, which depends on the coupling strength, gamma specifically, 2 gamma long, the system reaches a state where it is entirely $1 angle QMM, a complete flip. The memory cell has returned to its ground state, and the escaping field now contains a particle whose state reflects the information that was in the memory. Precisely. The information originally encoded in $1 angle QMM is now encoded in the state $1 angle HRD. It's a perfect, reversible unitary transfer. No information lost. The figure in the paper even shows the imprint strength decreasing over time as the radiation carries the information away.
That's incredibly powerful. It demonstrates that, at least in principle, a mechanism exists within the QMM framework for Hawking radiation to carry away the stored information unitarily.
It resolves the paradox at its core. The radiation isn't random. It's modulated by the memory stored in the space-time fabric.
This obviously has major implications for how we think about black hole thermodynamics, particularly entropy. The standard Beakenstein-Hawking entropy, SBHD, which is proportional to the horizon area, equation 38, can't be the whole story anymore.
It can't be. If information isn't lost, the entropy accounting needs to reflect that. QMM introduces the idea of an effective entropy. This is the standard Beakenstein-Hawking entropy, SBH, minus the entropy associated with the information currently stored in the QMM. Let's call it SecBH. So, SBHY.
The true entropy contributing to the black hole's thermodynamics is reduced by the amount of information being held in memory.
Exactly. And this correction term, 7LM, is crucial for upholding the generalized second law of thermodynamics, GSL.
The GSL states that the total entropy of everything outside the black hole plus the black hole's own entropy must never decrease. How does 7 ensure this?
Okay, think about evaporation. As the black hole radiates, its area dollar shrinks, so SBH decreases. This looks like it might violate the GSL.
Right.
But two other things are happening. First, the emitted Hawking radiation increases the entropy outside the black hole, delta south side. Second, as information is retrieved from the QMM memory and put into the radiation, the stored information entropy also decreases.
Ah, so the change in the black hole's contribution to total entropy isn't just the decrease in SBH, it's the change in 7F, which is delta SBH.
Precisely. The full GSL statement in the QMM framework becomes delta S total plus delta SBH, delta SQMN gigacurie dollars. The entropy increase outside is balanced not just by the area decrease, but by the fact that the information contributing to CQM is being transferred outside, adding to delta south side AC. Not just thermal entropy, but information entropy.
It's a complete accounting. The book's balance. Information moves from being counted in SQM inside to being counted in outside.
It's a fully unitary thermodynamic cycle. And this connects back to that interesting point about area versus volume.
Right. SXBH is proportional to area dollar, but QMM seems intrinsically volumetric.
The storage mechanism is volumetric. The information is stored in the individual quantum cells, $6, which are Planck-sized volumes. The total number of available memory cells in XUMM near the horizon would be roughly the horizon area dollars times some small radial thickness, delta RAFS, all divided by the fundamental volume unit, the Planck length cubed, SPMB33. So NQMM propto A eta stat RLP33.
So while the overall entropy might scale with area for thermodynamic reasons we don't fully understand yet,
the physical location and mechanism of the information storage in QMM is tied to the volume of these Planck scale cells in the bulk spacetime near the horizon. This is a really important distinction from other approaches like holography.
Excellent point and a perfect transition. Let's move into section 3, QMM in context. How does this framework stack up against the other big ideas out there for solving the information paradox?
QMM's unique selling proposition, I think, is that it aims to solve the paradox while preserving both unitarity, which we've seen, and the equivalence principle, which is often a casualty in other models.
Let's compare it first to the holographic principle and its most famous realization, the ADS-CFT correspondence. Holography generally suggests information inside a volume is encoded on its boundary.
Right. The idea is that the 3D bulk reality we experience might be fully described by a 2D quantum field theory living on some distant boundary surface. For black holes, this would mean the information is stored not inside, but somehow projected onto the event horizon or maybe even a boundary at infinity.
What are the issues with applying that directly?
First, the best understood example, ADS-CFT, works mathematically in anti-de Sitter, ADS space, a universe with negative curvature, a negative cosmological constant. Our actual universe seems to have a positive cosmological constant, making it closer to de Sitter DS space. Adapting holography rigorously to DS space is, well, it's an ongoing challenge.
And second, QMM fundamentally disagrees about where the information is stored.
Absolutely. QMM is staunchly volumetric. Information is stored locally in the 4D bulk spacetime where interactions happen, within the Planck scale structure. It doesn't rely on projecting information onto a lower dimensional boundary. This makes the QMM framework potentially more general, applicable regardless of the large-scale geometry of the universe, ADS, DS, or flat space.
Okay, next comparison. The more controversial ideas, like black hole complementarity and the associated firewall paradox.
Complementarity was an earlier attempt to save both unitarity and the equivalence principle. It suggested that an infalling observer and a distant observer have complementary, equally valid but seemingly contradictory descriptions of reality near the horizon.
But then came the firewall argument. AMPS, the authors, argued that if information must get out via Hawking radiation to preserve unitarity for the outside observer, then the entanglement structure near the horizon gets broken in such a way that it creates a firewall, a high-energy curtain of particles right at the horizon.
And a firewall is a disaster for the equivalence principle.
Right. The equivalence principle, a cornerstone of GR, states that falling into a black hole should feel completely unremarkable locally. Like floating in empty space, you shouldn't hit a wall of fire at the horizon.
A firewall would incinerate the infalling observer instantly. It's a violent violation. So complementarity seems seem to lead to this contradiction. You could save unitarity or the equivalence principle, but maybe not both.
How does QMM navigate this? It claims to save both. How does it avoid generating a firewall while still getting information out?
The key is where the information storage and retrieval happens. It's not a macroscopic sheet of energy at the horizon. It's encoded in the microscopic, Planck-scale, granular structure of space-time itself.
So the modifications are deep within the fabric, not a surface effect.
Exactly. The quantum imprints and their interactions are significant only at those incredibly high energies and small distances. For a macroscopic observer falling through the horizon, the affected space-time geometry remains smooth, just as GR predicts. The equivalence principle holds for the macroscopic observer.
But the underlying microscopic structure is carrying the information, and the outgoing Hawking particles interact with that structure unitarily.
Precisely. Unitarity is preserved microscopically within the QMM, while the macroscopic smoothness required by the equivalence principle is also maintained. QMM decouples the two issues by pushing the information storage down to the Planck scale granularity. This, I think, is one of its most compelling features.
It's a very elegant way to potentially sidestep the firewall problem. Now, what about more exotic ideas like ER equals EPR?
Well, the idea championed by Susskind and Maldacena that entanglement, EPR from Einstein-Podolsky-Rosen, is somehow equivalent to geometric connections, specifically Einstein-Rosen bridges or wormholes, ER.
So maybe the information escapes through a wormhole connecting the black hole interior to the outside.
That's the rough idea. Entanglement between the Hawking radiation outside and the particles inside corresponds to a geometric wormhole linking them. QMM offers a much more conservative approach, perhaps.
So.
It doesn't require postulating these complex, non-trivial topological structures like wormholes connecting the inside and outside. The information storage and retrieval mechanism is entirely internal to the standard spacetime structure, just relying on its quantum nature at the Planck scale via the imprints. It sticks closer to standard QFT principles interacting with a quantized geometry without invoking exotic topology.
Less plumbing required, maybe. Okay, one more comparison. Soft hair theories.
Soft hair theories propose that black holes might have subtle, low-energy hair fields associated with conserved charges corresponding to asymptotic symmetries of spacetime, like BMS symmetries. The idea is that information could be encoded in these soft hair modes at the horizon.
How does QMM differ?
QMM is much more comprehensive. Soft hair typically deals with information encoded via very specific, low-energy soft gravitons or photons associated with these symmetries. QMM, on the other hand, proposes a mechanism where all quantum interactions involving any field, not just gravitons or photons, and at any energy scale contributing to the black hole, leave an imprint.
So QMM provides a generic universal imprinting mechanism, not just one tied to specific low-energy symmetries.
Exactly. It's a much broader framework for how information gets embedded into the space-time structure near the horizon.
Okay, so to summarize this section, QMM positions itself as preserving core principles like unitarity and the equivalence principle more consistently than firewalls, avoiding the exotic topology of ER, EPR, and offering a more universal encoding mechanism than soft hair, all while working within a potentially more general framework than standard holography.
That's a fair summary. And underpinning all this is its consistency with established physics principles, which is section 3.2.
Let's quickly reiterate those. First, locality and causality. Does QMM involve faster-than-light signals or spooky action at a distance?
No. The fundamental interaction Hamiltonian is built from local terms. The imprint hand depends only on the field at the same spacetime, 0.60s. Interactions happen point by point.
So influences spread sequentially, respecting the light cone.
Correct. Causality is built into the structure. There's no need for non-local effects to ensure unitarity. The information transfer happens through local interactions between the field and the adjacent QMM cells.
And second, the big one for any theory touching gravity, general covariance. Does QMM respect Einstein's principle that the laws of physics should be observer-independent?
This is absolutely crucial and a major challenge for any theory that discretizes spacetime. QMM addresses this by ensuring that all the fundamental objects, the field operators, the imprint operators, the Hamiltonians, are constructed mathematically as proper scalars, vectors, or tensors under general coordinate transformations.
So even though the underlying reality is granular, the description of that reality, the physics, transforms correctly when you change your viewpoint or coordinate system.
That's the requirement. The physical predictions must be independent of the observer's coordinate choice. By building general covariance into the operator definitions of the Hamiltonian structure, QMM aims to ensure it aligns with this fundamental principle of GR.
It's trying to mesh the discrete quantum world with the smooth, coordinate-independent world of relativity.
A very difficult balancing act, but essential for a unified theory.
Okay, the theoretical framework seems compelling, consistent, and potentially avoids the pitfalls of other approaches. But physics is an empirical science. Section 4, observable consequences and testable predictions. How could we ever hope to see evidence for QMM? We can't exactly probe the Planck scale directly.
No, we can't build Planck scale microscopes, but we can look for the macroscopic consequences of the QMM's core mechanism, particularly the unitary information retrieval during black hole evaporation.
And the most direct consequence of information retrieval is
That Hawking radiation cannot be perfectly thermal. If it carries information, it must deviate, however slightly, from a pure blackbody spectrum.
So, prediction number 1, non-thermal signatures in Hawking radiation.
Exactly. The standard prediction for thermal radiation follows the Planck distribution, which depends only on the temperature $2. QMM predicts modifications to this. The particle number distribution at frequency omega would look slightly different.
How different? What's the mathematical signature?
The sources suggest the QMM interaction effectively introduces something like a chemical potential into the distribution formula. So instead of being proportional to $1, E bar omega kBth $1, it becomes proportional to something like gamma OBKH $1. Here, gamma omega is the gray body factor accounting for scattering near the black hole.
What does a chemical potential usually signify in thermodynamics?
It typically relates to the energy cost of adding particles, suggesting the system isn't in pure thermal equilibrium, but has some conserved charge or constraint. In this context, MoMI-QM basically acts as a mathematical label, a fingerprint, indicating that the emission process is being influenced by the stored information, preventing perfect thermalization.
So observationally, we'd be looking for deviations from the expected smooth black body curve, little wiggles, bumps, or asymmetries in the spectrum.
Precisely those. Tiny, information-induced spectral features superimposed on the dominant thermal signal.
And where would we look for these? We can't really study Hawking radiation from astrophysical black holes. They're too cold.
The best bet is hypothetical primordial black holes, PBHs. These are black holes that might have formed in the very early universe with much smaller masses.
Small enough that they could be evaporating now.
Exactly. PBHs with initial masses around 10-15 grams would be completing their evaporation today, potentially releasing bursts of high-energy particles, particularly gamma rays.
So we could use gamma ray telescopes?
Yes, advanced observatories like the upcoming Cherenkov Telescope Array, CTA, or existing ones like Fermi LAT, could potentially detect the final gasp of an evaporating PBH. Analyzing the energy spectrum of that burst for these predicted non-thermal deviations, these MU-QMN effects, would be a direct test of QMM or any theory predicting unitary evaporation. It's a long shot, but actively being pursued.
Fascinating. Okay, prediction 2, gravitational wave GW anomalies. How does QMM affect the ripples in space-time from merging black holes?
The idea here is that while the inspiral and merger phases are dominated by classical GR, the final stage, the ring down, where the newly formed single black hole settles into its final state, might be subtly affected by the quantum structure of its horizon, predicted by QMM.
The ringing black hole's sound might be slightly off-key due to the QMM structure.
Sort of. The gravitational waveform emitted during ringdown is predicted by GR to be a sum of damped sinusoids, with specific frequencies and damping times determined only by the final black hole's mass and spin. QMM suggests the underlying granular information-rich structure near the horizon could slightly alter these dynamics.
So the observed waveform wouldn't be pure GR.
It would be the GR waveform plus a small correction, plus delta HQMM plus delta HQMMPL might manifest, for example, as a slight change in the damping rates of the ringdown modes. Perhaps an additional damping coefficient, let's call it kappa, like in equation 53, modifying how quickly the oscillations decay.
And this would be measurable.
Potentially.
Yeah.
We're talking about incredibly precise measurements. But the current generation of gravitational wave detectors, LIGO, Virgo, Keck-Agree, and especially future ones like LISA in space or the ground-based Einstein telescope, are designed to achieve sensitivities where such tiny deviations in the ringdown signal might become detectable.
So analyzing the fine details of the ringdown phase of merger signals could provide an indirect probe of the near-horizon quantum structure proposed by QMMM.
It's another promising observational window into quantum gravity effects, leveraging these cosmic collisions.
Okay, prediction 3, the Page curve. This seems absolutely fundamental for confirming unitarity.
It really is. The page curve described how the entanglement entropy of the emitted Hawking radiation, let's call it SEND, should behave over the black hole's lifetime tail.
Entanglement entropy measures how much the radiation is quantumly linked to the remaining black hole.
Exactly. Initially, as the black hole radiates, the emitted particles are entangled with their partners that fell inside, so the need increases. If information were lost, non-unitary evolution, this entropy would just keep increasing until the black hole disappears.
But for unitary evolution,
For unitary evolution, the information must eventually come out. Don Page argued that the entanglement entropy must reach a maximum around the halfway point of the evaporation, the page time, T-page 9, and then decrease, eventually returning to zero when the evaporation is complete.
why does it decrease?
Because after the page time, the emitted radiation starts carrying out the actual information that was stored inside. It's no longer maximally entangled with a shrinking interior, it's becoming purified, carrying the information that purifies the total state. This downturn in the page curve, equation 51, is the definitive signature of information retrieval.
And QMM's retrieval mechanism, via the interaction with the Catter-Char, naturally produces this.
Yes, the QMM framework inherently includes the mechanism that transfers information from the internal QMM states to the outgoing radiation. This ensures that the radiation becomes information-rich after the page time, leading to the required decrease in entanglement entropy. Observing the page curve experimentally, perhaps through subtle correlations between late-time Hawking particles, would be a monumental confirmation of unitary evaporation and strong support for QMM or similar theories.
Right. So PBH spectra, GW ring downs, and the page curve are the main astrophysical and theoretical checks. Are there other potential avenues mentioned?
Yes, a couple of more speculative but interesting future pathways. One is looking for signatures in the cosmic microwave background, ZMB.
The afterglow of the Big Bang. How could QMM affect that?
If QMM interactions were active in the extreme conditions of the very early universe, perhaps during inflation, the quantum imprints left on the fabric of space-time back then could have seeded subtle large-scale fluctuations. These might manifest today as tiny, specific patterns of temperature variations, delta polarization in the CMB, that are not predicted by the standard cosmological model.
So looking for specific anomalous anisotropies and ultra-precise CMB maps from missions like Planck or future ones like Lightbird.
Exactly. It's searching for fossilized evidence of QMM physics from cosmic dawn. The other avenue is laboratory analogs.
Creating black holes in the lab.
Sort of. We can create systems, for instance, using Bose-Einstein condensates, BECs, or superconducting circuits where sound waves or electromagnetic waves behave analogously to fields near a real black hole event horizon. These setups can even mimic Hawking radiation-emitting phonons, sound quanta, instead of photons.
And you could potentially test QMM ideas there.
That's the hope. By carefully designing these analog systems, one could try to engineer an interaction mimicking the QMM imprinting and retrieval. Then you could look for the predicted consequences, like non-thermal correlations between the emitted Hawking phonons, or evidence of information transfer in a controlled, repeatable lab setting.
Tabletop quantum gravity experiments. That's exciting.
It offers a complementary path to astrophysical observations, potentially allowing much more direct tests of the underlying mechanisms, albeit in an analogous system.
This has been an absolute fascinating tour through a potential revolution in fundamental physics. Let's try to crystallize the main takeaway.
For me, the quantum memory matrix hypothesis represents a profound paradigm shift. It elevates space-time from being just a passive background to being an active, dynamic, information processing component of reality itself.
And in doing so, it offers a way to resolve the long-standing deep conflict between quantum mechanics and general relativity, the information paradox, without seemingly breaking the core rules of either theory.
That's the goal. It strives to preserve unitarity, the equivalence principle, locality, causality, general covariance, all the foundational pillars. It does this by proposing a concrete mechanism, quantum inference, stored in a granular spacetime that avoids many of the conceptual hurdles faced by firewalls or wormhole-based ideas.
And critically, it's not just philosophy. It makes specific, potentially testable predictions about Hawking radiation spectra, gravitational wave signals, entanglement entropy curves, maybe even CMB patterns or lab experiments. It opens up pathways for empirical investigation.
It suggests the solution isn't necessarily out there in extra dimensions or on distant boundaries, but might be woven internally into the very fabric of space-time at its most fundamental level.
Which leads us to the final, really mind-bending thought for you, our listeners, to ponder. If QMM or something like it is correct, What does it truly mean?
It means that every single quantum interaction that has ever happened anywhere in the universe, from the Big Bang's initial moments to particle collisions in stars to the chemical reactions in your own brain right now.
Every single one leaves a permanent, albeit incredibly subtle, quantum imprint on the structure of space-time itself.
Reality becomes its own ultimate recording device. Space-time is the hard drive.
So what are the implications for our understanding of memory, of history, of the past, if the universe quite literally forgets nothing? If the entire history of everything is encoded permanently in the quantum state of the space-time we inhabit?
The universe might possess an eternally perfect, indelible memory.
A cosmos that remembers everything. We'll leave you to grapple with that thought. Until next time on The Deep Dive. We are diving straight into the fire today, right where the biggest conflict in modern physics lives. Welcome back to The Deep Dive.
We're here to hand you those intellectual keys like always.
And today, we are wrestling with, well, the ultimate cosmic disagreement, the tension between the very small and the very large.
It's a big one. We're unpacking a really radical new theoretical proposal. It's called the quantum memory matrix, or QMM for short.
QMM. And it claims to solve the black hole information paradox.
That's the claim. And it does it by fundamentally changing how you view space-time itself.
It really is the ultimate grudge match, isn't it? You've got quantum mechanics, QM on one side.
Right, QM dictates all the rules for the microworld. Particles, fields, probability, superposition, all that weirdness.
And the most sacred rule in QM, unitarity.
Unitarity. It's basically the conservation law of information. Think of it like this. Unitary evolution means you can scramble the data, change its form, maybe hide it, but you can never fundamentally destroy the total amount of information that was there to begin with.
It's like a cosmic perfect balance sheet. Every entry must be accounted for somehow.
Precisely. No information gets truly deleted.
Okay. And then opposing it, we have general relativity, G.R. Einstein's monumental theory of gravity.
It's a geometric powerhouse. It works beautifully for describing the cosmos, planets, galaxies, stars collapsing.
And, crucially, black holes, which is exactly where the trouble starts.
Exactly there. GR tells us that once matter, or information, crosses the event horizon of a black hole, it's essentially lost to the outside universe forever.
Classically, anyway. All that's left to describe the black hole from the outside is its mass, its charge, and its angular momentum. Nothing else.
That's the famous no-hair theorem. It implies that all the intricate details, the quantum states of every single particle that formed the star that collapsed, supposedly erased, wiped clean, leaving only those three numbers: mass, charge, spin.
Okay, that already sounds like a catastrophic breach of the QM balance sheet right there.
It does. But the paradox, the real kicker, truly crystallizes when Stephen Hawking brings quantum effects into the picture, specifically near the horizon.
Hawking radiation. Right.
Correct. Hawking realized that due to quantum fluctuations near the event horizon, black holes aren't actually perfectly black or stable. They should slowly radiate energy.
And evaporate over, well, immense timescales.
Immense, yes. But here's the problem. This Hawking radiation, as originally conceived, arises from vacuum fluctuations just outside the horizon.
Meaning it's purely thermal.
Thermal, like the heat coming off a perfectly uniform hot object. It's statistically random.
It carries no specific information, no unique signature about what fell into the black hole in the first place.
Exactly. So if the black hole eventually evaporates completely, just vanishes.
Leaving behind only this random thermal static.
Then where did the original quantum information go? The detailed structure of the matter that collapsed, it seems to be gone forever.
And that is the flagrant violation of unitarity. QM says information cannot be lost. GR plus quantum field theory seems to predict it is lost in black hole evaporation.
That's the core of the paradox. You can even quantify the thermal output with the Hawking temperature, T sub h. The key thing isn't the exact formula, but that it's related inversely to the black hole's mass.
The smaller black holes are hotter, evaporate faster.
Right, but the radiation they emit is still modeled as basically information-free noise in the standard picture.
So we hit an impasse, a fundamental conflict. Either GR's description of a black hole's final state is wrong, or QM's principle of unitary is incomplete.
Something has to give.
Enter the quantum memory matrix. QMM. This hypothesis proposes a truly mind-bending way out.
It really is radical, it says. Space-time isn't just the passive stage for physics. It's not just the backdrop.
It's an active participant.
An active dynamic quantum information reservoir, the ultimate cosmic hard drive, essentially.
Wow. Okay. So our mission today in this deep dive is to really dig into the blueprints of this QMM framework.
We need to unpack how it digitizes space-time, how it defines these things called quantum imprints, and critically, how it sets up a concrete, unitary mechanism for getting the stored information back out.
Resolving the paradox, but hopefully while respecting the core ideas of both QM and GR.
That's the ambitious goal.
Okay, let's get into the foundations then. Section 1. Building the theoretical machinery of QMM. And the first, really fundamental step is throwing out smooth, continuous space-time.
Absolutely. That smooth fabric of GR-QMM says, nope, not at the smallest scales. The starting point is quantization. We have to assume space-time is discrete.
Discrete. How small are we talking?
We're going way down to the Planck scale. The Planck length, L sub p, is about 10 to the minus 35 meters. Incredibly tiny.
Almost incomprehensibly small.
Right. At that fundamental level, QMM proposes that space-time is broken up into fundamental, indivisible units. Think of them as space-time quantum cells, little building blocks of reality.
I get the picture of a granular structure, like pixels on a screen instead of a continuous image. But what does this mean mathematically? How do you describe the state of this pixelated spacetime?
Mathematically, it's quite powerful, actually. Each single quantum cell, let's label one as X, isn't just a point. It's associated with its own finite dimensional Hilbert space. Call it H sub X.
Okay, so each pixel has a quantum state space.
Exactly. And if you want to describe the state of the entire QMM, the whole fabric of spacetime, its total Hilbert space H sub QMM is formed by taking the tensor product of all those individual Hilbert spaces.
So H sub QMM equals the tensor product over all X of H sub X.
That's the one. It means the overall state of spacetime is this enormous, complex quantum vector defined by the specific quantum state of every single cell.
That sounds computationally nightmarish, but theoretically neat. Does this idea of discrete spacetime link up with other theories?
It does. It aligns very nicely, conceptually at least, with frameworks like loop quantum gravity, LQG, and causal set theory, which also explore discrete structures.
And does this discreteness give QMM any immediate advantages, technically speaking?
Oh, a huge one. A problem that plagues almost every attempt at quantum gravity. It provides an intrinsic ultraviolet regularization.
Okay, UV regularization. Let's unpack that term. What does that mean intuitively for us?
Right. So in standard quantum field theory, when you try to calculate certain quantities like how much energy is in the vacuum or how a particle interacts with itself, you often end up integrating over all possible energies, including infinitely high ones.
The ultraviolet part refers to high energy, short wavelength.
Exactly. And these integrals often blow up. They give you infinite answers, which physically don't make sense. These are called divergences. UV regularization is essentially a way to tame these infinities, to cut them off.
So how does QMM do that automatically?
Because space-time itself is discrete. There's the smallest possible distance, the Planck length. You can't have distances smaller than that.
And if there's a minimum distance, there must be a maximum possible energy or momentum.
Precisely. The Planck scale acts as a natural, physical, hard cutoff. You simply cannot cram infinite energy into a finite, discrete cell. This built-in limit prevents those divergences from ever appearing in the first place.
Making the theory potentially much better behaved. Finite results.
Finite, physically meaningful results. It sidesteps a major hurdle.
So we've got this granular stage, these quantum cells. What does this granularity actually do to physics? How does it manifest?
Well, it fundamentally changes geometry. Geometric properties we usually think of as continuous, like length, area, volume, are no longer continuous in this picture.
They become quantized. They can only take on specific, discrete values.
Exactly. Operators corresponding to length, let's say L hat or area, A hat or volume, V hat, now have discrete spectra. Their possible measurement outcomes are step-like, not smooth.
And the size of these steps, these quanta geometry, they depend on something called the Barbero-Emirzi parameter, gamma.
Yes, gamma. It's a dimensionless number that pops up in canonical quantum gravity, particularly LQG. Its precise physical role is still debated, but you can think of it here as a kind of tuning parameter related to the Planck length that sets the scale for the fundamental quantum of area or length.
So geometry itself is fundamentally lumpy at the Planck scale, and gamma helps define the size of those lumps.
That's a good way to put it. Distances and areas come in discrete packets.
All right, the stage is set and it's granular. Now the really new part, the quantum imprint. This is where space-time stops being passive and starts remembering.
This is the core mechanism. A quantum imprint, let's denote it I hat sub x, is basically a record, a memory trace of a quantum event, and it's encoded directly into the quantum state of the local space-time cell, x.
So when something happens at a point in space-time, like a particle interaction?
Right, say a quantum field phi hat of x interacts at that point x. That interaction causes a change, a transition in the state of the local Hilbert space h sub x. The space-time cell itself registers that the interaction occurred.
It gets marked somehow. And the nature of that mark, the imprint operator I hat sub x, must depend on the details of the field that caused it.
Precisely. The theory needs to specify how the imprint depends on the field. The source material gives an example form, particularly for a scalar field phi. The function f, which determines the imprint, could depend on the field's value phi hat, its gradient or derivatives, partial mu phi hat, its conjugate momentum.
They give a specific example structure, like f depending on phi squared and the derivative squared, like g0 times phi plus g1 times phi squared plus g2 times the derivative term.
Exactly that kind of structure. S of phi and its derivatives could look like g0 times phi of x plus g1 times phi squared of x plus g2 times partial mu phi of x contracted with partial mu phi of x, and maybe other terms too.
And those constants, g0, g1, g2, they're like coupling constants. They determine how strongly each aspect of the field gets imprinted.
Precisely. Think of what those terms represent. The g0 term, coupled just to phi x, might record the field's amplitude or strength at that point, just its presence.
Okay. And the g1 term, coupled to phi squared, that often relates to energy density, right?
It does. So the QMM could be recording the energy density of the field passing through that cell.
And the g2 term, with the derivative squared, that looks like kinetic energy or momentum information, how the field is changing or moving.
Exactly. So the space-time cell isn't just noting something was here. It's potentially recording what was here, amplitude, its energy density, and its state of motion or change. The specific imprint I hat sub x embeds these local characteristics of the field into the cell's quantum state via those coupling constants.
This really hammers home the idea of space-time as this universal, detailed hard drive, recording literally everything that happened.
Every quantum interaction leaving its tiny mark.
But how do we ensure this whole process, this constant writing to the space-time hard drive, doesn't violate that sacred rule we started with unitarity? How do we guarantee information isn't accidentally lost in this complex interplay?
That brings us to the crucial unifying structure, the total Hamiltonian of the system. You can't just look at the fields or the QMM in isolation anymore.
You have to consider the whole thing together.
The whole thing. The total Hilbert space, H total, is the tensor product of the field's Hilbert space and the QMM's Hilbert space. H field's tensor HQMM.
Okay.
And for the evolution of this combined system to be unitary, meaning information preserving the total Hamiltonian operator, H hat, that governs its evolution, must be Hermitian.
Hermitian means the operator is equal to its own conjugate transpose, a mathematical property that guarantees unitary evolution over time.
That's the key. So QMM has to be constructed such that the total H hat is Hermitian.
And this total Hamiltonian H hat, it's built from different pieces.
Yes, typically three main components. First, you have H hat subfields. That's just the standard Hamiltonian from quantum field theory that describes how the particles and fields evolve on their own kinetic energy, potential energy, standard interactions.
Makes sense.
Second, you need H hat sub QMM. This describes the internal dynamics of the space-time quanta themselves, how a quantum cell might evolve on its own or interact with its neighboring cells, like maybe a sum over individual cell Hamiltonians, H hat sub x, plus interactions between neighbors, sum over pairs x, y of H hat sub x.
So the space-time fabric itself might have its own internal dynamics.
It could, but the most critical piece for information transfer is the third term, H hat sub int, the interaction Hamiltonian. This is the bridge between the fields and the QMM.
This is where the imprinting actually happens, governed by the Hamiltonian.
Exactly. And its form is crucial for ensuring overall hermiticity. The source gives the form for the interaction at a point x, H hat int of x, as being the field operator phi hat of x, tensor product with the dagger, Hermitian conjugate, of the imprint operator I hat sub x, plus the Hermitian conjugate of that whole term, which works out to be phi hat dagger of x tensor product with I hat sub x itself.
So phi tensor I dagger plus phi dagger tensor I dagger.
Right. That specific structure ensures that H hat int is Hermitian. And if H fields in HQMM are also Hermitian, then the total Hamiltonian H hat is guaranteed to be Hermitian.
And therefore, the evolution of the combined system fields plus spacetime memory is unitary.
Precisely. Information isn't lost, it's just coherently transferred between the field degrees of freedom and the QMM degrees of freedom. The total information content of the combined system is conserved at all times. Unitarity is built in by construction.
Okay, we've built the machine, now let's apply it where it matters most. Back to the black hole, the source of the whole paradox. This is section 2, encoding and retrieval. Let's start with encoding. How does the information get into the QMM as the black hole form?
Right, the encoding phase. This happens during the gravitational collapse itself. As matter crushes down, forming the event horizon, the gravitational field becomes incredibly strong, the curvature intense.
And according to QMM, these intense conditions should drive equally intense interactions between the collapsing matter fields and the underlying space-time quanta.
Exactly. This is the ultimate imprinting event. The interactions described by H hat int become dominant near where the horizon is forming. The information carried by the collapsing matter gets forcefully imprinted onto the QMM cells in that region.
If we use that simplified model again, where the imprint operator I hat sub x is just proportional to the field phi hat of x, say I hat sub x equals g times phi hat of x, then the interaction Hamiltonian H hat int becomes something like 2 times g times the sum over all points x of phi hat of x tensor product with itself, phi hat of x.
That form really highlights the direct coupling, doesn't it? The field is essentially interacting with itself via the space-time medium, and the result of all this intense interaction during collapse is a profound
Entanglement.
entanglement between the infalling matter and the space-time fabric.
Yes. Let's say the initial state of the collapsing matter is some complex quantum superposition described by coefficients c sub n for different basis states n. And initially, the QMM is in some simple ground state. Let's call it 0 sub QMM.
So the starting state is product state. Psi field 0, tensor 0 QMM. Right. But after the collapse, after the intense H hat interactions near the forming horizon, the final state is no longer a simple product. It's an entangled state.
The information originally encoded in those coefficients Cn of the matter field
Is now shared. It's encoded in the correlations between the final state of the now trapped matter and the excited state of the QMM cells near the horizon. The QMM is no longer in its simple 0 state. Its state now reflects the Cn coefficients.
So the information hasn't vanished into a singularity or disappeared. It just changed address.
Changed address is a great way to put it. It's been transferred from the matter degrees of freedom to the QMM degrees of freedom. It's stored locally in the quantum states of the space-time cells in the vicinity of the horizon, preserved within the combined Hilbert space.
Okay, that handles the encoding side and seems to resolve the information lost during formation. But the real test, the heart of the paradox, is the evaporation, the retrieval phase. How does QMM get the information back out and imprint it onto the outgoing Hawking radiation?
This is the crucial payoff of the QMM framework. Remember, the standard picture says Hawking radiation particles, let's denote their creation operators as a dagger sub k, are created from vacuum fluctuations and are purely thermal.
Random noise.
QMM says no. As these outgoing modes, the Hawking particles, are created near the horizon, they must interact with the QMM cells that are holding the stored information before they can escape to infinity.
So there's another interaction process happening during emission.
Yes, and it involves what the authors call the cumulative imprint operator, I hat sub HR. You can think of this as representing the total stored information, maybe summed or averaged over all the imprinted QMM cells near the horizon region H.
Like the collective memory bank of the horizon.
Something like that. And the retrieval mechanism is governed by a specific retrieval, Hamiltonian H hat retrieval.
Okay, what does that look like?
Yeah. Its structure is designed to couple the creation and annihilation of Hawking particles directly to this stored information. It looks like a sum over all possible outgoing modes K. Each term involves the creation operator a dagger sub k tensor product with the cumulative imprint I hat sub HR, plus the Hermitian conjugate term, which involves the annihilation operator a sub k tensor product with I hat dagger sub HR. There are coupling constants gamma sub k in there too.
So roughly, gamma times act dagger tensor IHR plus gamma star times act tensor IHR dagger.
Exactly. Look at what this structure does. When a Hawking particle is created via a dagger K, it simultaneously interacts with the stored imprint, IHR. When a particle is absorbed via Eike, it interacts with the conjugate imprint, IHR dagger,
This coupling transfers the information.
and facilitates the transfer. As the particle is emitted, it picks up information from IHR, modifying its state so it's no longer purely thermal. The state of IHR also changes, reflecting the information that has been read out.
This is the absolute core of the solution. Let's really slow down and use that intuitive two-state system example from the sources. It seems critical for the aha moment. How does the information literally flip from the QMM back to the radiation?
Okay, great idea. Simplified dramatically. Imagine a single QMM cell near the horizon that holds one bit of information. It can be in state 0 sub QMM, clean, no imprint stored, or state 1 sub QMM, marked imprint present.
And we consider just one mode of outgoing Hawking radiation. Initially, there's no particle, so it's in the vacuum state 0 sub HR.
Right. Now, suppose the information is stored in the QMM cell. So the combined initial state before retrieval for this bit is 0 sub HR tensor 1 sub QMM. No radiation particle yet, but the memory cell holds the info.
Okay, initial state, no particle, memory full.
Now the retrieval Hamiltonian HAT retrieval starts acting. Think of it like a quantum beat performing a rotation of combined state space. It starts transferring the excitation or information from the QMM part of the state to the radiation part.
Like pouring water from one bucket to another.
Exactly. The probability amplitude of finding the system in the initial state, 0 HR tensor 1 QMM, starts to decrease over time, maybe following a cosine function, like cosine of gamma t.
And simultaneously, the probability amplitude of finding the system in the flip state where the particle has been created and carries the information, and the QMM cell is now clean, starts to increase.
Yes, that state would be 1 sub HR tensor 0 sub QMM. Its amplitude increases following a sine function, like sine of gamma t.
So particle created, memory now empty.
Precisely. And because of the way cosine and sine work, after a specific time interval, t equals pi divided by 2 gamma, where gamma is the coupling strength.
The cosine term goes to 0 and the sine term goes to 1.
Exactly. The system is perfectly transitioned. The probability of being in the initial state is 0. The probability of being in the final state, 1 sub HR tensor 0 sub QMM, is 1.
The information transfer is complete and deterministic for this simple system. The QMM cell returned to its clean state, and in doing so, forced the creation of a Hawking radiation particle that now carries the precise piece of information that was just erased from the space-time memory.
That's the essence of the unitary retrieval mechanism. It's not magic. It's a direct consequence of the engineered interaction Hamiltonian. The evaporation process is unitary because the information isn't lost. It's actively and coherently retrieved by the outgoing radiation through this interaction with the QMM.
This completely rewrites the thermodynamics of black holes, then.
Fundamentally, if the Hawking radiation isn't purely thermal, if it carries information, then the whole notion of black hole entropy needs revisiting.
The standard Beakenstein-Hawking entropy, S sub BH, is proportional to the area A of the event horizon. It's often interpreted as a measure of the information hidden behind the horizon.
Right, the information that seemed lost. But QMM introduces a crucial correction. There's the entropy associated with the information that isn't lost, but is actively stored in the QMM near the horizon. Let's call this S sub QMM.
So the relevant entropy is now an effective entropy.
Exactly. An effective entropy S sub F, which would be the Beakenstein-Hawking area term minus the entropy of the stored information. SEF, SSSBH, SQMM.
How does this play out during evaporation? As the black hole shrinks, SPH, proportional to area, decreases.
Yes, but simultaneously the stored information SQMM is being read out and transferred to the outgoing Hawking radiation. So SQMM is also decreasing.
And the entropy of the environment outside the black hole, outside, must be increasing.
It increases significantly. And importantly, it increases not just because it's receiving thermal energy, but because it's receiving the information encoded in the now non-thermal Hawking radiation. The entropy increase outside has both a thermal component and an information entropy component retrieved from SQMM.
And this is how QMM manages to uphold the generalized second law, GSL, of thermodynamics. The law that says total entropy must never decrease.
Precisely. The GSL involves the change in the black hole entropy, which is now Ceph, plus the change in the outside entropy.
Yeah.
So delta S total equals delta S outside plus delta SBH minus delta S QMM.
Okay.
In the standard picture without QMM, delta SQMM is 0, and delta S outside only gets the thermal part, leading to a potential decrease in total entropy if SBH shrinks the paradox, but with QMM.
The decrease in the store information entropy minus delta SQMM is perfectly compensated by the increase in information entropy carried away into S outside.
Exactly. The information leaving the QMM store appears in the outgoing radiation, so the total change, delta S total, remains greater than or equal to 0. The GSL is maintained naturally because information is merely transferred, not destroyed. The cosmic ledger stays balanced.
We should touch on that subtle point again. Area versus volume. Bekenstein-Hawking entropy SBH scales with the horizon area. But QMM stores information in these Planck scale volume elements, the quantum cells. How does that reconcile?
It's a great question. The key is that while the fundamental storage medium is volumetric, the NQMM quantum cells occupying tiny Planck volumes LP cubed, the information relevant for evaporation seems to be primarily stored in a thin shell or layer near the horizon.
So the number of relevant storage cells, NQMM, might be proportional to the horizon area A times some small characteristic thickness delta R, all divided by the volume of a single cell, LP cubed.
That's the idea. NQMM is roughly A times delta R over LP cubed. So the total number of memory bits scales with the area, even though each bit occupies a tiny volume. The macroscopic entropy, SBH or Ceph, emerges as an area law, but the underlying mechanism relies on volumetric storage within the granular structure near that area.
Right. That brings us neatly to section 3, QMM in context. Because, let's face it, the information paradox is arguably the biggest unsolved problem in fundamental physics. And QMM isn't the only proposed solution out there. How does it stack up against the competition?
Comparing is essential. QMM makes a strong claim. It aims to solve the paradox while rigorously preserving two fundamental principles that other approaches often struggle with, or even sacrifice.
Which are?
Unitarity, which we've established is built in via the Hermitian-Hamiltonian and Einstein's equivalence principle.
The idea that falling into a gravitational field feels locally like being in empty space, no drama at the event horizon for an infalling observer.
Exactly. Keep those two principles in mind as we compare. Let's start with the most famous alternative, the holographic principle, and its concrete realization in the ADS-CFT correspondence.
Holography. The idea that all the information in a volume of space can be encoded on its boundary like a hologram.
It's a profound and mathematically powerful idea. AD-SCFT provides a precise dictionary between a gravity theory and a specific type of spacetime anti-de Sitter space, ADS, which has negative curvature.
And a quantum field theory, CFT, without gravity living on the boundary of that space.
Right. Information in the bulk, ADS, is perfectly mapped to the boundary, CFT.
Yeah.
It elegantly handles information, but
our universe isn't anti-de Sitter. It seems to have a positive cosmological constant, making it more like de Sitter space. And holography fundamentally maps information away from the bulk volume to a lower dimensional boundary.
that's the key difference. QMM, by contrast, is designed to work within the actual four-dimensional bulk spacetime we seem to inhabit. The information storage is local and volumetric within the granular structure itself. It doesn't rely on assuming a specific background geometry like ADS or mapping info to a distant boundary. The memory is right here, woven into the fabric everywhere.
Okay, point QMM for applicability, perhaps. Now, what about the really controversial idea, firewalls?
Firewalls. These were proposed, in a sense, as a logical consequence of trying to preserve unitarity and locality within the standard framework of effective field theory near the horizon. If information has to get out, and locality holds, some argue it leads inevitably to a high-energy curtain, a firewall, right at the event horizon.
Which an infalling observer would slam into.
Exactly. And that's a dramatic, violent violation of the equivalence principle. Smooth infall is gone. You get incinerated at the horizon.
So firewalls save unitarity but kill the equivalence principle. How does QMM avoid this? It posits a granular structure near the horizon. Doesn't that also threaten smooth infall?
That's the crucial subtlety. QMM avoids the firewall issue because of the scale at which the information storage and retrieval happens. The quantum cells, the imprints, the interactions, they all occur at the Planck scale, 10 to the minus 35 meters.
These are quantum gravity effects, not classical barriers.
Precisely. For a macroscopic observer, or even a particle whose quantum wavelength is much, much larger than the Planck length, the spacetime still appears effectively smooth on average. The underlying granularity doesn't create a macroscopic energetic barrier like a firewall.
So the equivalence principle holds for infalling observers because the bumpiness is way too small to notice classically. But the microscopic quantum interactions are happening, allowing unitary information transfer.
That's the claim. Unitarity is preserved via the Planck scale interactions within the QMM, while the equivalence principle is preserved because those interactions don't create a macroscopic obstacle. It sidesteps the firewall dilemma.
Clever. What about other ideas like ER, APR? This conjecture links quantum entanglement, EPR pairs, with space-time geometry, suggesting they are connected by Einstein-Rosen bridges or wormholes.
ER. EPR is a fascinating mind-bending idea connecting geometry and entanglement. It suggests that entangled particles might be secretly connected by microscopic wormholes. In the black hole context, perhaps the entanglement between the interior and the radiation corresponds to wormholes allowing information out.
But it relies on these exotic topological structures, wormholes, which are still highly speculative.
Right. The potential advantage of QMM is that it offers a mechanism for information retrieval without needing to invoke wormholes or drastic changes in space-time topology. The information transfer happens via local quantum interactions with the memory matrix. No non-local wormholes required.
And finally, how does QMM compare to the idea of soft hair? The notion that black holes might indeed have subtle, long-range hair in the form of zero-energy graviton or photon fields at the horizon, which could encode the information.
Soft hair is interesting because it identifies specific, measurable quantities at the horizon, these soft charges, that do retain some information. However, it's generally thought that soft hair alone might not be sufficient to capture all the information of the collapsed matter. It mainly accounts for low-energy, long-wavelength aspects.
Whereas
QMM proposes a mechanism that encodes information from all quantum interactions, high energy, low energy, all types of fields, into the local space-time structure. It's potentially a much more comprehensive information storage system than just relying on soft zero-energy modes at the boundary.
So, to wrap up this comparison section, let's reiterate the fundamental principles QMM seems to uphold robustly.
Two big ones we haven't stressed enough yet: locality and causality. The way the interaction Hamiltonian H-hat int is constructed is crucial. The imprint I-hat sub x at point x depends only on the field phi-hat at that same point x.
No spooky action at a distance. Interactions are point-like.
Exactly. Information propagates causally, respecting the light cone structure. There's no instantaneous communication assumed between different parts of the QMM or the fields.
And the second big one, general covariance.
Yeah.
This is the bedrock of general relativity physics, shouldn't depend on your coordinate system.
Absolutely non-negotiable if you want compatibility with GR. All the operators, the Hamiltonians, the imprint structures in QMM must be formulated as proper scalars, vectors, or tensors. This ensures that the physical predictions of the theory are independent of the observer's viewpoint or how they choose to label spacetime points. It maintains the geometric spirit of GR.
Okay, this QMM framework sounds theoretically elegant, consistent, and it tackles the big paradox while respecting core principles. But, physics is an experimental science. A theory needs testable predictions. So, Section 4, observable consequences. Where can we actually look for evidence of QMM?
This is where QMM becomes really exciting, because the proposed solution, the information retrieval mechanism, directly implies observable deviations from the standard picture. If Hawking radiation isn't purely thermal, we should be able to see the difference.
Prediction number 1, non-thermal signatures in Hawking radiation. So we're not expecting a perfect black body spectrum anymore.
Exactly. We should look for small characteristic deviations, wiggles, bumps, asymmetries in the energy spectrum of the emitted particles that wouldn't be there if it were purely thermal noise.
How does the math capture this? You mentioned an effective chemical potential earlier.
Right. The standard Planck distribution for thermal radiation depends only on temperature. The number of particles n at a given frequency, omega, is proportional to 1 over e to the power of h bar omega over kBth minus 1 times the gray body factor, gamma of omega.
Okay.
QMM modifies this. The interaction with the memory matrix introduces a bias, effectively acting like a chemical potential. Let's call it most sub QMM. This mo QMM term depends on the information being retrieved.
So the formula changes.
The denominator changes. It becomes e to the power of h bar omega minus mqmm, all over kBth, then minus 1. That minus mqmm in the exponent is the key signature.
It shifts the distribution slightly, making it non-thermal. It favors certain energies over others, depending on the information content.
Precisely. MQMM is the smoking gun for information retrieval, imprinted onto the radiation spectrum.
But how on earth could we measure such a tiny effect? Astronomical black holes evaporate incredibly slowly.
We need to look for black holes that evaporate quickly. That means very small ones. The best candidates are primordial black holes, PBHs, hypothetical black holes formed in the extreme conditions of the very early universe.
Some of which could be small enough to be evaporating now.
Exactly. If PBHs with the right initial mass exist, those evaporating today would be releasing bursts of high-energy particles, particularly gamma rays.
So we need gamma-ray telescopes.
Very sensitive ones. Instruments like the Cherenkov Telescope Array, CTA, currently under construction, or existing ones like the Fermi Gamma Ray Space Telescope, could potentially detect the final gamma ray flash from an evaporating PBH.
And if they can measure the energy spectrum of that flash?
And find it deviates from a pure thermal spectrum in a way consistent with that MUN-QMM term, that would be incredibly strong evidence for QMM, or at least for unitary evaporation involving information retrieval.
Okay, that's one avenue. What about gravity itself? QMM modifies space-time structure. Does it affect gravitational waves? GWs?
It should, particularly in the most extreme gravitational events, black hole mergers. When two black holes collide and merge, the final combined black hole settles down into a stable state.
This settling down produces the ring-down signal in the gravitational waves, like a bell being struck.
Exactly. The frequency and damping time of that ring-down signal in standard GR depend only on the final black hole's mass and spin, the no-hair properties.
But if QMM is correct, the near-horizon structure isn't perfectly smooth GR. It's granular, it holds memory. That should affect the ring-down.
It should subtly alter how the merged hole settles. The predicted gravitational waveform, HGA, wouldn't be just the pure GR waveform, HGRT. There should be a small correction term added.
Yeah.
Delta, HQMMT.
Equals HTRT plus delta HQMMT. And what form might this correction take?
It could manifest as changes to the ring-down frequencies, or perhaps more likely, changes to the damping rates. The QMM structure might provide additional ways for the merger energy to dissipate or oscillate. The sources mention this could be characterized by an additional damping coefficient. Let's call it kappa.
So kappa represents extra damping due to the interaction of the gravitational perturbations with the QMM's granular memory-filled structure.
That's the idea. The oscillations might die out slightly faster, or in a slightly different way, than predicted by pure GR because of this underlying quantum space-time structure.
Again, this sounds like an incredibly subtle effect to measure.
It absolutely is. But the precision of gravitational wave detectors is constantly improving. Current detectors like LIGO, Virgo, Keck-Rai are already probing the ring-down phase.
And future ones.
Future ground-based detectors like the Einstein telescope, and especially the planned space-based detector LISA, Laser Interferometer Space Antenna, will have vastly greater sensitivity. They are being designed specifically to make ultra-precise measurements of black hole mergers, including the ring-down. Finding tiny deviations consistent with QMM's predictions, that extra kappa perhaps would be a huge discovery.
A different kind of signature using gravity itself. Now, there's also the overall theoretical benchmark for unitary evaporation, the Page curve.
Ah, yes, the Page curve. This is less about a specific signal and more about the overall pattern of information release. It describes how the entanglement entropy of the accumulated Hawking radiation should behave over the black hole's entire lifetime if the evaporation process is truly unitary.
Entanglement entropy, measuring how much the radiation is entangled with the remaining black hole. What does the curve look like?
If information were lost, non-unitary, the entanglement entropy would just keep rising and rising as the black hole shrinks because the radiation remains entangled with degrees of freedom inside that eventually disappear.
But for unitary evolution,
For unitary evolution, the curve must follow a specific path predicted by Don Page. It starts at RO, increases initially as the black hole radiates and becomes entangled with the radiation. It reaches a maximum at a time called the Page time, T-Page, which is roughly when the black hole has lost half its initial entropy or half its mass.
and then, this is the crucial part.
Then, the curve must turn over and start decreasing. As the black hole continues to evaporate past the Page time, the outgoing radiation starts carrying out the information that purifies the earlier radiation. The entanglement between the radiation and the now shrinking black hole decreases, eventually hitting zero when the black hole disappears completely.
So initial rise, peak at T-Page, then a fall back to zero. That turnover is the absolute signature of unitarity.
It is. If information comes back out, the Page curve must turn over. The QMM's retrieval mechanism, where the radiation actively reads out the stored memory, provides a concrete physical process why the curve turns over. It ensures the radiation emitted after T-Page purifies the system.
Measuring the full Page curve for an astrophysical black hole seems impossible, given the timescales.
Practically impossible, yes. But the principle is key. Detecting any evidence that the Hawking radiation is carrying information, like the non-thermal signatures, my QMM, is indirect evidence that the Page curve would be followed if we could measure it. It validates the core unitary function of QMM.
Okay, besides black holes, are there other places QMM might leave a trace? The sources mentioned future experimental pathways.
Yes, a couple of exciting possibilities. First, looking back to the very early universe and the cosmic microwave background, CMB.
The afterglow of the Big Bang. How could QMM affect that?
If QMM interactions and printing were happening during the universe's earliest moments, perhaps during cosmic inflation, those primordial quantum imprints on spacetime itself could have seeded subtle variations in the CMB.
Like specific patterns in the temperature fluctuations or polarization.
Exactly. We might look for tiny anisotropies, variations across the sky represented by delta TQMM as a function of direction, theta, phi, or specific polarization patterns that don't quite fit the standard cosmological model, but could be explained by these lingering space-time memory effects from the dawn of time.
Are current or future CMB experiments sensitive enough?
It's pushing the limits, but missions like the Planck satellite have already provided incredibly detailed maps. Future experiments like Lightbird aim for even higher precision, particularly in polarization. It's a long shot, perhaps, but finding such a primordial signature would be revolutionary. Fossil evidence of quantum memory.
Wow. And the second pathway is closer to home. Laboratory analogs.
This is a rapidly growing field and very exciting. Scientists can create systems in the lab that mimic certain aspects of black hole physics, even though they don't involve actual gravity.
Like using ultra-cold atoms, Bose-Einstein condensates, BECs, or perhaps superconducting circuits.
Precisely. You can set up flows or potentials in these systems that create an effective event horizon for sound waves in BECs or electromagnetic signals in circuits. These systems are predicted to emit an analog of Hawking radiation.
So we can study Hawking radiation in a controlled lab setting.
We can study the quantum mechanics of particle creation near an effective horizon. And the key question is, can we design experiments where an analog of information is stored near the horizon and then retrieved by the analog Hawking radiation?
Testing the QMM mechanism conceptually, even without gravity.
Exactly. Observing QMM-like information transfer, seeing non-thermal correlations in the analog radiation that mirror the page curve logic in a controlled lab experiment that would provide powerful evidence for the conceptual validity of the QMM framework. It would show the proposed type of quantum interaction is possible.
Well, this deep dive into the quantum memory matrix has been quite the journey. It's a phenomenal look at how physics might finally reconcile the micro and the macro, QM and GR.
It really forces a fundamental shift in perspective, doesn't it? Taking space-time from just being the passive background, the stage.
And making it an active player, an information storing component woven into the fabric of reality.
And the theoretical strength of the QMM framework, as presented, seems to lie in its potential elegance. It aims to resolve that central conflict, the information paradox, by integrating gravity's geometry with quantum information conservation.
All while trying hard to preserve the equivalence principle, which is huge.
And locality and causality. It suggests the path towards quantum gravity might involve fully embracing the idea that space-time is fundamentally granular, and crucially, that it has memory.
And importantly, as we just covered, it's not just philosophy. It offers concrete, scientifically accessible predictions. Maybe subtle, maybe hard to find, but testable.
Those potential spectral shifts in gamma rays from PBHs, the tiny modifications to gravitational wave ring downs, maybe even patterns in the CMB or verification in lab analogs. These make QMM a viable scientific pathway, not just speculation.
A testable route towards potentially understanding quantum gravity.
It's a powerful underlying idea, taking information, arguably the most fundamental concept in quantum mechanics, and literally embedding it into the structure of reality itself.
So as we wrap up, we want to leave you, our listeners, with that final provocative thought that the source material hints at.
If this quantum memory matrix hypothesis or something like it turns out to be correct, think about the implications.
It would mean that every single quantum interaction that has ever occurred in the history of the universe,
from the Big Bang through star formation, planet formation,
to the incredibly complex quantum processes happening in biological systems, maybe even in our own brains.
Every single one leaves a permanent, perhaps incredibly subtle, but indelible quantum imprint on the very fabric of space-time itself.
If space-time is, quite literally, the ultimate hard drive of the cosmos, a universal memory bank, what does that truly mean for our understanding of history, of memory itself? Does the universe truly forget anything?
It suggests perhaps it doesn't. The past might be encoded everywhere, all the time, in the finest details of reality.
A profound thought to ponder. We'll see you next time on The Deep Dive. Welcome back to the deep dive. Today we're wading into, well, probably the deepest water in theoretical physics, that treacherous meeting point where quantum mechanics, QM, just slams into general relativity, GR.
It's a fundamental clash, isn't it?
Yeah.
Especially when you look at black holes. That collision zone is where we find one of the most stubborn puzzles out there.
Absolutely. The black hole information paradox. It's been this persistent headache for decades.
Yeah.
It forces us to question things we thought were bedrock, like quantum unitarity.
It really does. And it suggests maybe our picture of space-time itself needs a serious overhaul.
Which brings us to our mission today. We're doing a deep dive into a really fascinating proposal trying to bridge this gap, the quantum memory matrix hypothesis, or QMM. We're working primarily from the paper, The Quantum Memory Matrix, a unified framework for the black hole information paradox.
Right, and the core idea is pretty radical, isn't it?
It is. It flips the script. Instead of space-time being this passive background, this empty stage, the QMM suggests it's an active player, a dynamic quantum thing that actually stores information.
Like a cosmic hard drive, built into the fabric of reality itself.
Exactly. Using what the authors call quantum imprints down at the tiniest possible scale, the Planck scale. But before we get into how QMM works, we really need to feel the weight of the paradox it's trying to solve. Why is this information loss problem so critical?
Okay, let's break it down. From Einstein's general relativity, black holes are surprisingly simple, almost featureless beasts. You know, the famous no-hair theorem.
Right. Once something collapses past the event horizon, all the intricate details are just gone, erased.
Pretty much. The resulting black hole, according to GR, is completely defined by just three numbers. Its total mass, its electric charge, and its angular momentum, or spin. Nothing else.
So you could throw in, I don't know, an encyclopedia set written in qubits, or just a lump of structureless iron of the same mass, and from the outside, the final black hole looks identical in terms of its gravity and electromagnetism.
That's the GR picture. Pure simplicity. The trouble starts, the paradox kicks in, when you bring quantum mechanics into the picture, specifically Stephen Hawking's discovery of Hawking radiation.
Ah, yes, the faint glow from the edge of darkness.
Exactly. Hawking showed that due to quantum effects near the event horizon, these virtual particle pairs constantly popping into existence, black holes aren't truly black. They should slowly radiate energy away.
And eventually they completely evaporate, right?
That's the prediction. They leak energy, lose mass, and shrink, potentially disappearing entirely over vast timescales. But the killer detail in Hawking's original calculation was the nature of this radiation.
It was thermal. Perfectly, utterly thermal.
Precisely thermal, meaning it follows a perfect black body spectrum, determined only by the black hole's temperature, which in turn depends only on its mass, charge, and spin, just like the black hole itself.
Okay, why is thermal the dirty word here? What's the problem with that?
Because thermal radiation is fundamentally random, statistical. Think about a hot piece of coal. The heat radiating off it tells you its temperature, sure, but absolutely nothing about, say, the intricate crystalline structure of the coal before it burned. It's information-free in that sense.
So the Hawking radiation carries no memory, no details about the specific quantum states of whatever fell into the black hole in the first place. The encyclopedia versus the iron lump, the radiation is the same.
Exactly. According to the semi-classical calculation, the radiation is purely thermal, meaning it's a causal, carrying zero information about the unique quantum properties, the superpositions, the entanglement, the specific coefficients to star, defining the initial state of the stuff that formed the black hole or fell into it later.
Okay, I see the collision now. The black hole forms, swallowing neat quantum information. Then it evaporates by emitting purely thermal information-free radiation, and the black hole is gone.
Poof, gone entirely.
So where did the original quantum information go? If the radiation didn't carry it out, and the black hole doesn't exist anymore, it seems like it was just deleted from the universe.
And that is the paradox. Because a cornerstone principle of quantum mechanics is unitarity. It fundamentally states that information cannot be destroyed. Every quantum process, in principle, must be reversible. You should be able to run the film backwards and recover the initial state.
But if the black hole evaporation deletes information, you can't run the film backwards. Unitarity is violated, quantum mechanics breaks down.
That's the crisis. It's a deep, fundamental conflict between GR's description of black holes and QM's insistence on information conservation. We desperately need a mechanism, some physical process, that allows black holes to evaporate while somehow preserving and returning the information.
And this is where the quantum memory matrix steps in, proposing a mechanism built into space-time itself.
Exactly. It claims to be that missing piece.
Okay, let's transition them. Section 1. Digging into the QMM hypothesis itself. The foundational shift, as you said, is making space-time an active participant. How does that work? What's the first principle?
Well, the absolute bedrock of QMM is the quantization of spacetime. It proposes that spacetime isn't the smooth, continuous background sheet that GR assumes. Instead, when you zoom way, way down to the Planck scale, which is incredibly tiny, about $6 together times 1035 meters.
Like unimaginably small.
Truly. At that scale, QMM posits that spacetime itself is granular, discretized. It's made up of fundamental indivisible units. The authors call them spacetime quanta, or quantum cells.
So it's less like a smooth fabric and more like a mesh or a very, very high-resolution digital screen.
That's a good analogy. Think of it like moving from analog film, which seems continuous, to a digital image made of discrete pixels. Each pixel here is a fundamental quantum cell of spacetime.
Okay, and these aren't just points. They have quantum properties.
Yes, crucially. Each quantum cell, let's say located at a position $6, isn't just a geometric point. It possesses its own internal quantum state space, its own finite-dimensional Hilbert space. We denote this as math-Gallen state, that's script h sub x.
So each tiny point in space-time has its own little quantum playground.
In essence, yes. And because the entire fabric of spacetime is built from these cells, the total quantum state space of the entire quantum memory matrix, the space where the memory resides, is formed by combining all these individual playgrounds. Mathematically, the total Hilbert space, math-Gallen HQMM, script HQMM, is the tensor product of all the individual cell Hilbert spaces math-Gal for all $6.
Right, the tensor product bigatime math-Gal XX. That means the total state space can be vastly larger and more complex than the sum of its parts, allowing for entanglement between the space-time cells themselves.
Precisely. It creates this incredibly rich underlying quantum structure to spacetime.
Now, if space-time is fundamentally discrete, built of these quanta, that must have immediate consequences for geometry itself, right? Things like length, area, volume. They can't be continuous anymore.
Exactly. This is a key feature and connects conceptually to frameworks like loop quantum gravity. If spacetime is granular at the Planck scale, then geometric observables must also be quantized. They must come in discrete chunks, not continuous values.
So, like, there's a minimum possible length.
Yes. The QMM framework, drawing from these ideas, posits operators for geometric quantities. For instance, the length operator, let's call it LL, is expected to have a discrete spectrum. Its eigenvalues, the possible results of a length measurement, would likely be proportional to the Planck length. All dollars may be scaled by some constants like the Barbero-Emirzi parameter, gamma, which often appears in these theories.
So you can't measure a length smaller than a certain fundamental unit. It's like space has the smallest possible tick mark on its ruler.
That's the conceptual picture. It naturally introduces a physical cutoff, preventing the infinities that often plague quantum field theories when you try to probe arbitrarily small distances. It provides what physicists call a natural UV regularization.
And this extends to area and volume, too.
It does. The area operator, similarly, would have a discrete spectrum. In models inspired by LQG, its eigenvalues often depend on sums involving quantum numbers, typically spin quantum numbers, denoted GR. You often see terms like the square root of GR times G plus D to 1.
Those DM numbers, they're not just abstract math, are they? They represent something physical.
In the LQG context, they represent the quantized flux of the gravitational field lines piercing through the elementary area patch. So the area itself becomes a measure of how many fundamental quantum threads of gravity are linking through that surface. Since these G-draw values are discrete, half integers usually, the possible area values are also discrete.
Wow, okay, so area isn't just a smooth quantity, it's fundamentally about counting these discrete gravitational links. That's a very different picture of geometry.
It's geometry emerging from underlying quantum information. And similarly for the volume operator, had V. Its spectrum is also expected to be discrete, depending on related quantum numbers. The big takeaway is, QMM starts with the premise that spacetime is quantum and granular, and this very granularity is the key to its function as a memory system.
Okay, so we have this quantized, granular spacetime. Now, how does it actually record information? What exactly is this quantum imprint the paper talks about?
Right, the memory part. A quantum imprint is defined as a localized modification, a change to the internal quantum state of one of those quantum cells, math crawls. This change is induced when a quantum field interacts at that specific spacetime point $6.
So if a particle, represented by some quantum field xz of xe, zips through a particular quantum cell, it doesn't just pass through unchanged, it leaves a mark.
It leaves a physical trace, exactly. The interaction isn't passive. It actively alters the state within math-C. Think of it like writing a bit of data onto that cell.
And this writing process is described mathematically.
Yes, by the imprint operator, denoted half-a. This operator acts on the Hilbert space of the cell. This specific form depends on the local properties of the field that's doing the interacting.
What color properties?
Things like the field value itself, but also its derivatives, like partial mu half hat of x, which relate to the field's momentum or how it's changing across space-time, and potentially its conjugate momentum, half of x, which relates to energy density.
So the imprint captures various aspects of the field's state at that point.
Yes. The source gives an example form for what half-a might look like for a simple case, like a real scalar field. It's not just a simple proportionality.
Right, I see it here. It could be something like, okay, let's break it down. Maybe a term proportional to the field itself, like $d hack.
Right, $d times phi hat of x. So the strength of the field leaves a mark.
Plus maybe a term proportional to the square of the field, like $d and 2x and 2x.
G dollars times phi hat squared. So perhaps something related to the field's energy density at that point.
And maybe even a term involving the derivatives, like G-2 times partial mu hat contracted with partial mu phi.
Exactly, G-2 times partial mu phi times partial upper mu phi. That term relates more to the kinetic energy or the stress energy components of the field.
And these G-pill and G1, G22 are coupling constants. They determine how strong the writing is.
Precisely. They define the strength and the nature of the encoding. How sensitive is the space-time cell to the field's amplitude versus its energy density versus its momentum, and so on. The critical point is that the quantum state of the matter field gets actively encoded, imprinted, into the state of the underlying space-time quantum cell at that location.
It's not just passing through, it's fundamentally altering the medium. That's the bridge.
That's the bridge. It's the mechanism by which information transitions from the matter field into the structure of space-time itself.
Okay, now section 2. We have the mechanism for encoding, but the absolute core goal here is preserving unitarity, right? Making sure information isn't actually lost overall. How does QMM guarantee this?
This is where the mathematical framework has to be really rigorous. We now have two interacting quantum systems. The ordinary quantum fields, like matter and radiation, and the quantum memory matrix, the space-time cells.
So the total state isn't just the field state anymore, it's a combined state.
Exactly. The full description of the system lives in a larger combined Hilbert space. Let's call it math-LH total. This is the tensor product of the Hilbert space for the field and the Hilbert space for the QMM, math-GIL QMM, in its total times math-GIL product. Tensor product again, meaning the state can involve entanglement between the fields and the space-time structure itself.
Absolutely essential. Now, the evolution of any state in this total Hilbert space must be unitary. Quantum mechanics demands it. And unitary evolution is generated by a Hermitian Hamiltonian.
Right. The Hamiltonian operator, hat, which represents the total energy, must be self-adjoint, meaning hat must equal its Hermitian conjugate, dagger. This guarantees that probabilities are conserved and the evolution is reversible.
Precisely. So, the QMM framework defines a total Hamiltonian that governs the entire combined system, and it has to have the right structure. The paper writes it as a sum of 3 key parts: Hat's fields plus hat QMM plus hat.
Okay, let's break that down. Hat fields is presumably just the standard Hamiltonian for the quantum fields themselves, describing how they propagate and interact with each other.
Correct. That's standard quantum field theory. Hat QMM would describe the internal dynamics of the quantum memory matrix itself. Maybe how adjacent quantum cells interact or evolve even in the absence of matter fields. This part is less specified, but it also needs to be Hermitian.
But the really crucial piece for information transfer, for the encoding and potential retrieval, must be the interaction term. That's the bridge. That's the absolute key. This Hayden describes how the fields talk to the space-time cells, how the imprints are made, and for the total Hamiltonian headed to be Hermitian, assuming headage fields in Hemienses, this interaction term here must also be Hermitian.
That's the non-negotiable constraint for unitarity. How is Hayden constructed to guarantee that? It needs to describe writing information in, but also allow for reading it out right. That smells like conjugate terms.
You've got it. The interaction has to be symmetric in a way that allows for reversibility. The interaction Hamiltonian is typically defined as a sum over all space-time cells $6. So head at x is the local interaction at cell sextol.
And that local term has a structure.
The structure proposed ensures this hermeticity. It looks like this. Head x, header x stubs. O times head and x.
Okay, let's unpack that. We have the field operator tensored with the Hermitian conjugate of the imprint operator, happen x, plus the Hermitian conjugate of the field operator, hatna, tensored with the original imprint operator, hapna.
Exactly. Look at the symmetry. The first term might represent, loosely, the field influencing the QMM via hatmakers, while the second term represents the QMM potentially influencing the field via hatten, involving the conjugate field operator hatnak. This structure, where you have a term and its Hermitian conjugate added together, is precisely what guarantees that hatten is itself Hermitian.
Ah, because the conjugate of hatnag is hatnagar, and the conjugate of a sum is the sum of conjugates. So if you take the conjugate of the whole hat expression, you get it right back. It's self-adjoint by construction.
Precisely. And it simplifies nicely in common cases. For a real scalar field, the field operator is self-adjoint, meaning half-fidag. And if the imprint operators are also defined to be self-adjoint, which seems physically reasonable for representing stored information, then hat-fidagger's half.
In that case, the interaction simplifies to something like $2. Wait, no, it just becomes hat fee plus hat fee. No, that's not right. The structure hat fee dagger is inherently Hermitian, regardless of whether A and B are Hermitian themselves. Let's recheck. If hat fee dagger, then hat fee, and hat fee x2, then hat fee plus 2 dex. Yes, okay. And that is Hermitian because hat fee and hat fee are assumed Hermitian. The general form guarantees it anyway.
Right. The general form is the key constraint. By ensuring hat is Hermitian, the total Hamiltonian hat is Hermitian, and the time evolution operator OUT is unitary. Information is conserved by the fundamental dynamics. That's the mathematical guarantee against information loss.
Okay, so the math holds up. Let's picture it now. Matter falls into a black hole. Let's say it's described initially by a quantum field state. Heddy's field, zero wrangle, which is a superposition, maybe some C and inner wrangle fields. The crucial information is encoded in those complex coefficients, the eta step.
Right, and let's assume the QMM, the space-time structure, starts in some simple initial or ground state, P to C or wrangle, maybe just D or wrangle till. So the total initial state is just the product. Hannigan wrangle fields, no entanglement yet. But as this matter approaches the black hole or crosses the horizon, the interaction Hamiltonian eta becomes significant and starts acting on this state. Exactly. Even a small-time evolution, say using first-order perturbation theory, shows that the state evolves to something like Diffie wrangle-wrangle-ite.
Right.
When you apply a juth, which contains terms like tan times hanch is null, it acts on both parts. The half-thea part acts on the field state in the wrangle field, so the half part acts on the QMM state per beta wrangle.
Precisely. The result is no longer a simple product state. It becomes an entangled state. Schematically, it looks something like some Q-wrangle-wrangle, where the QMM part Neukart is now modified, imprinted, based on the original field state Merwrangle fields and the operator at Judge.
And crucially, those original coefficients, the part which held the quantum information, they are still there. They now dictate the correlations, the entanglement between the state of the field and the state of the QMM. The information hasn't vanished. It has been transferred from being solely encoded in the field superposition to being encoded in the entanglement pattern between the field and the space-time structure.
So the quantum coherence isn't destroyed, it just moves. It shifts residence from the matter degrees of freedom to the space-time degrees of freedom via these imprints. The space-time literally remembers this superposition.
That's the core of the encoding mechanism. Information is stored locally in the quantum states of the space-time cells near where the interaction happened, likely near the event horizon for a black hole.
Okay, storage secured. Unitarity maintained during infall. But that's only half the story. The black hole eventually evaporates via Hawking radiation. How does the QMM ensure the information gets out again? The retrieval mechanism must be just as crucial.
Absolutely. If the information stays locked in the QMM forever as the black hole disappears, we still have a problem. So there must be a retrieval phase. During the emission of Hawking radiation, the outgoing particles, the radiation modes, must interact with the QMM in a way that extracts the stored information.
So the Hawking radiation process itself isn't purely thermal in this picture. It's modulated by the stored memory.
Exactly. The QMM framework proposes a retrieval interaction. Let's think about the outgoing radiation modes.
Mm.
These are created by operators, typically denoted Hot-Dagger, where Takaloro labels the mode like its frequency and angular momentum.
So Dagger creates a particle of Hawking radiation.
Right. Now, this creation process isn't happening in a vacuum. It's happening near the horizon, where the QMM holds the stored information from whatever fell in earlier.
Hmm.
So there needs to be an interaction Hamiltonian for retrieval, let's call it a hash rate.
And this retrieval Hamiltonian must couple the outgoing modes to the stored information in the QMM.
Precisely. But the outgoing particle doesn't just interact with a single imprinted cell. It likely interacts with the collective state of the QMM near the horizon. So the concept of a cumulative imprint operator, HR, for Hawking radiation, is introduced.
What defines that? Is it just the sum of all the relevant imprints?
Essentially, yes. It represents the total integrated memory stored in the QMM region relevant to the Hawking emission process. So HR would be something like sum is math call, where the sum is over all the quantum cells in the near horizon region, math call.
Okay, so this HR holds the collective memory. How does it interact with the outgoing radiation?
The retrieval Hamiltonian Harish retrieval is constructed, again, to be Hermitian to ensure unitarity. It typically takes a form involving terms that couple the creation and annihilation of radiation modes to this cumulative imprint, something like Hatcher-Dagger plus Gamma Catch-Up plus Gamma Catch-R.
Let's break that down. We sum over all possible outgoing modes $2. For each mode, we have a term where creating a particle is coupled to the memory, scaled by some coupling constant gamming stores. And then we have the Hermitian conjugate term, where annihilating a particle is coupled to the conjugate of the memory, scaled by the complex conjugate coupling gammic.
Exactly. This structure ensures Hatrick retrieval is Hermitian. And look what it does. When a Hawking particle is created, its state becomes entangled with the state of the cumulative memory.
So the state of the emitted particle is now correlated with the information stored in the QMM.
Precisely. The interaction effectively reads the information from Neukart and encodes it into the state of the outgoing radiation particle.
Clever.
As more and more particles are emitted, the complete information originally stored in the QMM is gradually transferred into the correlations within the outgoing Hawking radiation.
Which means the radiation isn't perfectly thermal anymore. It has subtle correlations, subtle deviations from pure randomness that carry the information about what fell into the black hole.
That's the solution to the paradox. The information isn't lost, it's encoded into the QMM during infall, and then retrieved, imprinted onto the correlations within the Hawking radiation during evaporation. Unitarity is preserved throughout the entire life cycle of the black hole.
Okay, that's a beautifully complete picture. Encoding, storage in space-time, retrieval via modulated Hawking radiation, all governed by Hermitian Hamiltonians, ensuring unitarity. It hangs together really well mathematically. But, the landscape of information paradox solutions is crowded. We've had firewalls, fuzzballs, remnants, holography. What makes QMM stand out? Why is it potentially a better approach than some of these others?
Well, a major selling point, emphasized in the source, is QMM's strict adherence to principles that other proposals sometimes have to bend or even break, specifically locality and causality, and crucially, GR's equivalence principle.
Let's start with locality. Why is that a sticking point for other ideas?
Getting the information out of the black hole is the hard part. Some early ideas, and even some aspects of later ones, seem to require some form of non-local interaction like information, somehow instantly jumping from deep inside the black hole to the outgoing radiation, faster than light, violating causality, or needing correlations between regions that are causally disconnected.
Spooky action at a distance, but applied to black holes?
Kind of, yeah. QMM avoids this entirely because the fundamental interaction is local. The imprint sand depends only on the field on at the same point $6. Information is stored where the interaction happens, and retrieval also happens via local interactions near the horizon. Everything propagates within the light cone. No, there's no need for non-local magic.
Okay, that's a big plus. Now, the equivalence principle, this is the idea that falling into a large black hole should be uneventful at the horizon, right? Free fall is free fall.
Exactly. An observer crossing the event horizon shouldn't feel anything special, shouldn't encounter a wall of fire or some dramatic boundary. This is where the firewall proposal, famously put forward by AMPS Almary, Marolf, Polchinski, and Sully, ran into serious trouble.
Right. They argued that if you demand unitarity and also assume certain standard entanglement properties for Hawking radiation, you inevitably end up with a highly energetic, destructive firewall right at the horizon.
Which would completely violate the equivalence principle. An infalling observer would hit this wall and be instantly incinerated. That's a radical departure from general relativity's prediction of a smooth crossing.
So how does QMM handle this? Does the infalling observer feel the imprinting process?
No, and that's the beauty of it. The QMM mechanism operates at the Planck scale. The imprints are modifications to the quantum state of the spacetime cells, this ultra-fine granularity. But the macroscopic geometry, the smooth curvature described by GR that the infalling observer experiences, remains essentially unperturbed.
So the information storage happens at a level far too small to affect the classical trajectory or experience of someone falling in.
Precisely. The observer sails smoothly across the horizon, just as GR predicts, completely unaware that the quantum details of their constituent fields are being meticulously recorded in the Planckian structure of spacetime around them. QMM preserves both unitarity and the equivalence principle.
It's like the difference between hitting a brick wall versus having your passport photo discreetly taken as you walk through a gate. One is violent, the other leaves the passage smooth, but records information.
That's a great analogy. Now compare this to another major contender, the holographic principle, often explored through the ADS-CFT correspondence.
Holography suggests information isn't stored in the volume at all, but on the boundary, right? Like a 3D image stored on a 2D hologram.
That's the core idea. Information about a region of space, the bulk, is encoded on its lower dimensional boundary, typically scaling with the area, like the event horizon area for a black hole. ADS-CFT provides a concrete mathematical realization of this, but usually in anti-de Sitter, ADS, spacetime, a specific type of negatively curved universe.
Which is not the universe we live in. Our universe seems to be flat or slightly positively curved to Sitter-like, especially on large scales.
Right. Applying ADS-CFT directly to realistic black holes in our universe is mathematically challenging and often requires significant assumptions or approximations. QMM, on the other hand, offers a different picture.
It's inherently volumetric, isn't it? Information is stored within the quantum cells occupying the bulk volume near the horizon.
Exactly. It's a fundamentally four-dimensional mechanism operating within the space-time volume, not projected onto a boundary. This makes it potentially more directly applicable to our observed universe without needing exotic geometries.
But wait. The Bekenstein-Hawking entropy, the measure of black hole information capacity, famously scales with the area of the horizon, not the volume. How does QMM reconcile its volumetric storage with the area law?
That's a subtle but crucial point discussed in the source. While the storage medium is volumetric, the quantum cells math aches, the total number of active cells involved in storing the information near the horizon might still effectively scale with the area. The paper suggests the number of relevant QMM quanta, nen QMM, could be related to the area times some small radial thickness delta r near the horizon, divided by the fundamental Planck volume LP3 to nose.
Okay, so 9 QMM propto A times delta RLP33. Because the Planck length ER power is involved, and entropy often relates to the logarithm of the number of microstates, you can potentially recover the LPM upcast scaling of the Bekenstein-Hawking entropy from this microscopic volumetric count within a thin shell.
Exactly. QMM provides a potential microscopic origin for the area law entropy. By counting the underlying volumetric quantum degrees of freedom of space-time itself, they get excited or imprinted near the horizon. It connects the macroscopic area law to the microscopic Planck scale structure.
So it complements holography rather than directly contradicting the area law result.
You could see it that way. It offers a concrete mechanism within the volume that ultimately respects the information bound set by the area.
What about other ideas like black hole remnants? The idea that evaporation stops, leaving a tiny Planck-sized nugget holding all the information.
Remnants are another proposed way to save unitarity. The information just stays locked inside this stable remnant. But they come with their own host of problems. For instance, how can a tiny Planck-sized object store the potentially vast amount of information from an arbitrarily large initial black hole? This leads to issues with predictability, potentially infinite pair production of remnants, and violations of entropy bounds.
QMM avoids that entirely.
Yes, because in QMM, the black hole does evaporate completely, but the information is returned coherently via the modulated Hawking radiation during the evaporation process. There's no need for a problematic remnant storing information indefinitely. It offers a complete, continuous cycle of encoding and retrieval.
Okay, QMM sounds conceptually elegant, consistent with core principles, and potentially avoids pitfalls of other theories. But elegant math isn't enough in physics. We need testable predictions. What are the observable signatures? How could we actually tell if QMM is the right picture?
This is where it gets exciting, moving from pure theory towards potential observation. The most direct consequence of the QMM retrieval mechanism is that Hawking radiation cannot be perfectly thermal.
Because it's carrying information via those correlations we discussed.
Exactly. So prediction number one, the energy spectrum of Hawking radiation should show small but potentially detectable deviations from the perfect black-body Planckian distribution predicted by the original semi-classical calculation.
We should see a fingerprint of the stored information in the outgoing light or particles.
Precisely. The QMM framework predicts that the particle number distribution, let's call it nu omega, for particles with energy bar omega, gets modified. The standard thermal distribution is given by no omega free, where nullars is the Hawking temperature, and gamma omega is the gray body factor that accounts for backscattering near the black hole.
Right, that's the standard formula. How does QMM change it?
It introduces an effective chemical potential, let's call it no QML, into the exponential term. The modified distribution becomes no omega nega EBT.
Ah, okay. So the energy bar omega is effectively shifted by this new Mn term in the exponent. What does this chemical potential represent physically?
This Mukrem term is a direct consequence of the interaction between the outgoing modes and the information stored in the QMM. It parameterizes the deviation from pure thermality. A non-zero chemical potential means the emission isn't purely random. It's biased or modulated by the stored information, leading to subtle shifts or asymmetries in the observed energy spectrum.
So if we could measure the spectrum of evaporating black holes with enough precision, we could look for this deviation, this effective chemical potential signature.
That's the hope. The prime candidates would be primordial black holes, PBHs, hypothetical small black holes formed in the very early universe. If they exist and have masses in the right range, some might be evaporating completely today, emitting high-energy particles like gamma rays.
So future gamma-ray telescopes with extremely good energy resolution might be able to see this non-thermal signature from PBH evaporation.
It's a long shot, observationally very challenging, but it's a concrete prediction. Finding such deviations would be incredibly strong evidence for information retrieval and potentially for the QMM mechanism itself.
Beyond the spectrum, does QMM make predictions about the pattern of information release over time?
Yes, it should be consistent with the Page curve. Don Page famously argued that for unitarity to hold, the entanglement entropy of the emitted Hawking radiation shouldn't just increase indefinitely as the black hole shrinks.
Right, entropy usually increases. What should it do instead?
The entanglement entropy should initially increase, as you'd expect when the radiation becomes entangled with the remaining black hole. But then, crucially, around the halfway point of the evaporation, the Page time, the entropy must reach a maximum and then decrease, eventually going back to zero when the black hole has fully evaporated.
Why does it have to decrease?
Because if information is being returned, the later Hawking radiation must be entangled not just with the remaining black hole, but also with the earlier Hawking radiation that already escaped, carrying the other half of the entangled pairs that fell in. This purification process, where the radiation becomes increasingly self-entangled and less entangled with the now disappearing black hole, causes the entropy to decrease. QMM, by returning information coherently, naturally predicts this Page curve behavior for the entanglement entropy. Observing this turnover would be another major piece of evidence.
Okay, so spectral deviations and the Page curve target the Hawking radiation itself. Does QMM predict anything on the gravitational side, things we might see with, say, LIGO or Virgo?
Potentially, yes. This is the second major observational avenue, anomalies in gravitational waves, particularly from events like black hole mergers.
How would the quantum structure of space-time affect macroscopic gravitational waves?
The idea is that the true gravitational waveform that we detect might not be exactly what pure classical general relativity predicts. There could be tiny corrections due to the underlying quantum nature of space-time, as described by QMM. So the observed signal would be delta t plus HQMM plus delta HQMMT.
A small quantum correction, delta HQMM, added to the classical GR waveform. Where in the signal would we expect to see this? The merger itself is incredibly complex.
Right. The inspiral and merger are highly nonlinear and messy. The source suggests, and this is common in searches for quantum gravity effects, that the best place to look for such subtle deviations is in the ring-down phase.
That's after the two black holes have merged, when the single distorted final black hole is settling down into a stable Kerr black hole.
Exactly. The ring-down is like the black hole ringing like a bell. It emits gravitational waves at specific frequencies and damping times, quasi-normal modes, characteristic of the final black hole's mass and spin. This phase is much cleaner and better understood theoretically than the merger itself.
So the QMM correction, delta HQMA, might manifest as light shifts in those ring-down frequencies or damping times compared to the pure GR prediction. Or maybe extra unexpected modes.
That's the kind of thing researchers are looking for. Parameterized tests of GR during ringdown are actively searching for exactly these kinds of small deviations. Finding a consistent anomaly that could be attributed to something like QMM's quantum space-time structure would be revolutionary, directly linking quantum gravity ideas to gravitational wave observations.
We'd need incredible precision from LIGO, Virgo, Kager, and future detectors like LISA or the Einstein telescope.
Absolutely. We're talking about extremely subtle effects. But the potential payoff probing quantum gravity observationally is enormous.
And one last potential signature mention, taking us back to the very early universe, the cosmic microwave background.
Yes, this is more speculative, but the idea is that if space-time has this fundamental granularity described by QMM, these effects would have been dominant in the ultra-high energy environment of the very early universe, possibly even during inflation.
Could that leave a fossil imprint on the CMB, the afterglow of the Big Bang?
Potentially. The standard model of cosmology, lambda CDM, predicts a very specific pattern of temperature fluctuations, delta T, in the CMB, primarily Gaussian and nearly scale invariant. If QMM effects were active then, they might have introduced additional subtle fluctuations, perhaps specific non-Gaussian signatures or other anisotropies, represented by a correction term delta TQMMM.
So the observed fluctuations would be delta T lambda CDM plus delta TQMM.
Something along those lines. Searching for these kinds of subtle deviations from the standard predictions in the CMB data from Planck, WMAP, and future missions is another potential, albeit indirect, way to probe the quantum structure of space-time proposed by QMM.
Wow. So from evaporating primordial black holes to merging stellar mass ones, and even the echo of the Big Bang QMM offers potential fingerprints across cosmic history.
It really ties together microphysics and cosmology in a compelling way.
Okay, let's try to wrap this up then. We've taken a deep dive into the quantum memory matrix hypothesis. It proposes a pretty radical solution to the black hole information paradox.
Yeah, the core idea is shifting space-time from just being the stage to being an active participant, a quantum memory bank.
Right, using these quantum imprints on discrete space-time cells at the Planck scale to locally store information that falls into a black hole.
And the whole framework is built around a carefully constructed Hermitian Hamiltonian, which is absolutely key. It guarantees that the total evolution encoding, storage, retrieval conserves information, satisfying quantum unitarity.
And it manages this, crucially, while respecting locality and causality, and preserving GR's equivalence principle, which avoids the whole firewall problem.
It also offers a volumetric storage mechanism that seems compatible with our 4D universe and provides a potential microscopic basis for the Bekenstein-Hawking area law entropy, connecting the volume granularity to the area bound.
Plus, and this is vital, it makes concrete, testable predictions. We're not just talking philosophy here.
Exactly. Deviations from a perfect thermal spectrum and Hawking radiation, that effective chemical potential of Uni-Argel, consistency with the page curve for entanglement entropy. And those potential tiny anomalies, the delta HQMN, in the ring-down phase of gravitational waves from mergers, maybe even CMB signatures, these are things we can actively look for.
And there's a nice theoretical bonus you touched on earlier, the discretization itself.
Oh, right. By postulating that space-time is fundamentally granular with a minimum length, the Planck length, QMM automatically provides a physical cutoff. It tames the infinities, the ultraviolet divergences that often pop up in quantum field theory calculations when you integrate over arbitrarily small distances or high momenta. The integrals become naturally finite because there's a limit to how far you can push them. It's mathematically cleaner.
It resolves a mathematical headache almost as a side effect of its physical premise. Okay, so it's a compelling package. It addresses the paradox, respects core principles, offers testable predictions, and has some mathematical elegance.
It's definitely a framework worth taking seriously in the quest for quantum gravity.
Which leads us to our final provocative thought for you to ponder. If space-time is this vast quantum hard drive constantly recording interactions via these imprints, what about the really, really old data? Could the quantum state of space-time around us today hold residual memories, imprints, from the very earliest moments of the universe? Perhaps even from before the Big Bang, if such a concept makes sense. Could the history of everything be written into the fabric of reality itself, waiting for us to develop the technology or the theory to finally read it?
A mind-bending possibility. If space-time remembers, what ancient secrets might it hold? The search for those quantum fingerprints continues.
Indeed it does. We hope you enjoyed this deep dive into the quantum memory matrix. Join us next time on The Deep Dive.